Okay, so I think we'll start in the interest of trying to remain on time. I know there's folks in transit who are not here yet, and this is going to be taped, so they'll all have the chance to listen to it. The other thing is a number of folks have told me that they would really like to hear today's presentations, but they're not able to be here for travel or other reasons, so that's the reason that we're going to tape this and let people see it afterwards. So my name is Mike Fritzy, and I'm from the Vice President of the Potomac Institute for Policy Studies. I had the pleasure of having lunch with our speakers today and explained a little bit about Potomac, but I thought I'll spend like maybe 2 minutes explaining what a think tank like ours is. Like, what does a think tank actually do, so people understand what we do and why we're holding this event. We are the Science and Technology think tank. We are an independent think tank. This means we don't take money from the industry deliberately in order to be very honest about our opinions of things, of strategies. We are a nonprofit think tank. Like I like to say too, that doesn't mean that we can lose money, but it means profit isn't our main goal. And we're also a nonpartisan think tank, so we don't play one political position or another. So those are sort of our founding principles. We focus on science and technology. The main thing that we do is we provide strategic advice on the impact of science and technology on government policies to departments and organizations in the U.S. government. Often we deal with very senior people who want to look at long-term strategies. There's new technologies coming along. I don't have to mention the folks about AI and 5G and all the other things that are going to have privacy, for example. They're going to have major policy implications. So we give advice on those areas driven from a scientific perspective, driven from a nonpartisan scientific perspective. And we found that that's a fairly unique service that is in demand. So the government needs this kind of thing. One of the things that we do when we look at science and technology policies, we really like bold ideas. We like to go for long-term, paradigm-changing, big thoughts. And on that area, we do internal work to look and to study and to look at those big thoughts. We have an internal think tank process called CREST, which looks at those things. And we also put on occasionally seminars and workshops that look at the future of areas that are ready to make a big paradigm change. This particular workshop came out of one of the discussions inside. I personally am a microelectronics geek, so that's a field that I'm particularly interested in. But as an institute, we were talking with the CEO who was very interested in where is the world going to go in terms of electronics paradigms now that the scaling, we all know that the Moore's law scaling, is coming to an end. And we've had like 50 years of incredible progress. That's coming to an end. What's coming afterwards? Not just incrementally what's coming afterwards. What are the big ideas for what's coming after Moore's law and the scaling? I remember when during most of my career, I had a roadmap booklet on my shelf. And I could pull out that roadmap booklet, and yeah, it was updated every once in a while, but you could have a rough idea of what was going to happen like every few years in terms of technology insertions, right? And this is no longer the case. The ITRS roadmap was dissolved, right? The committee that worked that was dissolved. I think Paolo is still working on its successor. Paolo Gardini is still working on its successor. But the point is now, it's wide open what's coming afterwards. Right? What is coming after this scaling alternative? And now when people argue between 5 and 4 nanometers, I just smile. So I'm like, what's the difference between 4 nanometers and 5 nanometers? Much less the nodes don't really have a physical meaning anymore for those of us who are in this field for a long time. So really it's time for some big ideas about where the future of electronics is going, what new paradigms are going to be enabled by that, and even for our personal interests, what does that mean for government policy? Right? What should government policy do in terms of research and the applications areas that government gets involved in? What should government strategies be? And so I'm really happy that we have a tremendous list of speakers here on this topic. They're all good communicators and they're all deep thinkers on the post-Moore landscape. They're all available in the little handout I gave you, but I'll make some introductions. I'll start with the keynote speaker first, Stan Williams. I guess I first met Stan when I was at DARPA, and I knew about your Memristor work, right, and the analog, I guess you can call it sort of analog computing paradigm. Really shaking things up a bit, right, in the conventional world about how to do computing with different kinds of lumped elements, or a new kind of lumped element. So Stan had a long and successful career at HP and in the quantum science group. He's now at Texas A&M, but still very interested in computing, like the long-term future of computing and novel concepts in computing. I don't want to read your long, august biography. I know you're extremely well known, and we're really happy that you took some time out to come here to talk. I just want to introduce you that, we have Dr. Stan Williams here, and he's going to give us a keynote on his perspectives on the future of the microelectronics. So Stan, I'll get out of your way.
All right, thank you very much. So is this loud enough that you can hear me all right?
Yes.
Okay. And the video recorder. I used to be a professor, actually of chemistry, many years ago at UCLA, where I was lectured to 350 students, and I never mic'd up then. So I actually prefer not to be electronically amplified, since that actually causes me to lose energy. All right, so what I'm going to do is talk about something that I've been thinking about and working on, and have seen what I will call a phase change in terms of my thinking and the entire community's thinking in this area over this past year. And that's computing using, I'll call it, brain-inspired dynamics. So you just heard from Mike. I'll call it the era of computation is changing. It's much less about computing numbers to 30 significant figures, and it's much more about what's the probability that something is going to occur. So people are interested in collecting and sorting information. They're interested in being able to control very complex systems in real time, searching for and identifying people, places, and things, finding hidden correlations in massive amounts of data, things that a human being just simply can't even grasp, but things out there that are moving around and changing. And this is actually very important in medical, financial, scientific, in a large number of areas. And then optimizing processes in a changing and uncertain environment. This is really critical. We have a body of knowledge, but there's continually new knowledge coming in. So how can you take what you know and be continually updating it and making decisions on the fly based upon in this very dynamic environment? So more scaling, one way or another, it's over. But what I claim is that it's ending at just the point in time where we've got addicted to big data. So we are collecting so much data now that we can't possibly move it around or analyze it. In fact, I've seen estimates that 95% of the data that we're collecting never gets looked at, never gets analyzed, and probably 80% of it is discarded within 3 hours. So here we're gathering this gigantic amount of information, and we're not doing anything with it. I mean, we're gathering data, but we're not doing anything with it. It's not turning into data. We're not learning anything from it. And the reason is because we're so limited in terms of our computation. The number of bits of data is increasing exponentially faster than we can manufacture transistors. So we can't beat this system by building a better transistor. And so my approach to this has been to try to understand and build devices that can replace thousands of transistors. So I'm not trying to build a better transistor, I'm trying to replace blocks, circuits, containing thousands of them in order to be able to go at this. And instead of looking at digital information, ones and zeros, look at analog information, look at real numbers, okay? So my goal is not to sort of increase the number of parts on a chip, is to increase the efficiency of those parts, make them vastly more efficient for our computing systems. And my primary inspiration in this is the brain, which is known to be the most efficient computational engine that we know about. And so I'm trying to learn what I can about the brain. Now, there's an interesting issue. What form of logic does a brain use? I mean, in other words, how do we make decisions? How do we plan future events? No one knows. There's actually no clear idea of exactly how we do that. There's ideas about how we learn and how we recognize things, but not how we plan, not how we think about things. So there's a lot of ideas floating around out there. But actually, the thing that's starting to coalesce, many papers are now saying this, is that intelligent organisms seem to be doing some sort of Bayesian inference. In other words, they've got a body of knowledge that they've assigned probabilities to. You get new events coming in, and so you update your probability analysis of what's going on based upon this type of process. I actually did not believe that at all until I talked to a Chinese researcher that I know, and he said he had 4 words for me. It made me change my mind completely. So now I'm sort of in the Bayesian camp. However, I'm not exactly sure that the answer is just Bayesian inference. I think actually it's probably some combination, or maybe even some larger type of construct that may include several of these things. And the main issue is that brains are nonlinear dynamical systems, and so they don't have a clock. They're always working on together, in a very high parallel fashion, and they're continually learning, storing memories, and performing logic. So this is essentially the type of structure that I'm looking at. So there's actually a strong historical connection between neuroscience and computing, and it goes all the way back to Pavlov. And so here's a great plot of many of the various types of neural networks that you've been hearing about that have come up over the years. And some people did a really good analysis of this, and just by looking at papers and tracing back citations, they were able to trace all of this back to Pavlov, essentially, and other work. And so the fundamental basis for most of the neural network stuff that's going on is 100 years old. There have been a relatively small number of things that have been coming out of later work in neurophysiology, and in particular, the DARPA Synapse program, which I think you may hear a little bit more about, using spiking and the True North chip is one of them. But for the most part, deep learning, this wonderful thing that you hear about, is actually based on 100-year-old science, and it's actually the most primitive of all of the types of networks that people are talking about. So it's actually very simplistic. And that's why it works, because you're able to compute essentially using mainly linear algebra. And so people are working on linear algebra accelerators. However, there are a couple of other branches on this tree, which are down here, where these types of networks are vastly superior to a sort of these deep learning CNN types of systems. And that's well known, but of course, you have to pay for it. And so the computational complexity of these types of systems down here is they're highly nonlinear. So the computational complexity is much worse than deep learning. And so the size of a problem that you can analyze using these more powerful systems is much smaller. And so my goal is to is to essentially flip things around. I want to make systems that are vastly more efficient, power-wise, and also faster, in order to be able to implement and perform these types of more powerful networks. Now, the issue is, again, I said that I'm not exactly sure that brains exactly behave like a Bayesian inference machine. And so here's an example that I like to show. Human beings are actually fairly clever. We can operate outside of the rules. Like, I never color inside the lines, right? And so let's think about 2 rooms. Say there was an electrician who wired up lighting in this room, and then by mistake wired up the switches in a different room. All right, so we've got 3 switches and 3 lights. And what you're asked is, okay, visit room A and B only once each, and map switches 1, 2, and 3 onto lights X, Y, and Z. A mathematician will tell you this is impossible. It's not computable. However, if you turn on 2 switches, wait a little while, then turn one of them off, go into the other room, and touch the 2 off light bulbs, one of them is warm. Okay? And so you can solve this problem. A human being can solve this problem because we cheat. We don't follow mathematical rules. So, you know, the issue is don't let computation be limited by formal mathematical definitions. So I essentially, you know, any way that I can cheat this problem, I do. I do that. So I'm going to talk about neuromorphic computing, this thing about being brain-inspired. It turns out that probably every person in the world working in this field has their own definition of neuromorphic computing. So there's no, I'll call it standard definition of it. So I tend to use the word brain-inspired. But my goal is not to reproduce the brain. I don't care about that. That's not what I'm trying to do. Other people are, but not me. What I want to do is I just want to build much better computers that humans can use as tools. You know, hopefully to amplify the capabilities. So let's just take a look at what the state of the art is. Oops. So here's the state of the art. I believe. Comes out of China. This is a chip called Tianji. It was on the cover of the August 1st issue of Nature. Okay? And you can sort of just see from their introductory graphic in this paper that was, you know, front page of Nature and made news literally all over the world, that you know, their goal is robotics. You know, their goal is robots that can actually you know, think for themselves. But if you look backwards at what they've done, they've actually combined two different types of system in one chip. So the Tianji chip is capable of performing spiking computing, like the True North chip, but it also can do regular convolutional neural networks in the same circuitry at the same time. So you can have, in this one chip, you can have two different types of, I'll call it neural type inspired computation going on at the same time and in a very, very power efficient way. Now why do they do something crazy like that? Well, so here's the example. Let me see if I can figure out how to get this thing going. Okay, so here is Tianji riding a bicycle. All right, so this is one chip operating on a small amount of battery power. Most of the power is going toward actually moving the bicycle. I can't even ride a bicycle that slowly. And yet the Tianji chip is able to make the bicycle go and keep it stable. And it's using the spiking network for that. Now look at this. That system was not programmed to do that. All right? It just saw that there was a barrier up there, figured out that it couldn't get through it, and went around it. Okay, in order to keep following this guy that's following. And now, in order to prove that Tianji wasn't just simply following the lines, this guy he's crossing over lines, and so Tianji is focused on him. But well, and one thing that didn't show up on that video very well, there was somebody else running the other direction, and Tianji was focused on the person that it was following. It didn't get distracted by the other person. Now, if you weren't impressed by that, I don't know what I can do. You know, there's nothing else that I can say. This is a lot harder than driving a car. A lot harder. And they're doing it with one chip running on a few volts and less than a watt. So if you look at this, so here is the sort of comparison table with the technologies that existed at the time the paper came out. And so you see that they're actually competing, you know, with True North and Loihi in terms of spiking neural networks, but they're also able to compete against the various specialty chips that have been built for doing CNNs and deep learning type of issues. And what you see is that the Tianji chip essentially beats everything that the other chips do in every category, sometimes not by a lot, but it beat everything, all right? But there's something else to realize. It's 3 years old. There's already a new generation of Tianji chip out. In fact, 36 hours ago, I was in Beijing. I attended a conference, the Nature Conference on Neuromorphic Computing. It was actually from on Monday through Wednesday of this week. Why was this conference held in Beijing by the journal Nature? Well, it's because most of the high-quality papers they're getting on neuromorphic computing are coming out of China. China is essentially submitting more papers to Nature in this area than the rest of the world combined. All right? There might be a reason for this. So another generation, what I learned at the conference was there's already another generation of Tianji that's been taped out, and it's expected to be at least 2 orders of magnitude better performance than the one that you just saw. And the plan at Tsinghua University is to build a supercomputer, essentially a large data center, based on Tianji chips, and open it to the world. And essentially let anybody who wants to use it, and they will teach you how to program it and everything else, because their idea is that they're going to start selling it. Now this is going to be their entryway into the commercial market in this area of neuromorphic computing. They are unashamed to state publicly that by the year 2030 they want to dominate the world's electronics markets. All right. Now, okay, Tianji's great. It's amazing. Could we improve on it? Well, the answer is, I wouldn't even put the question up there if I didn't think we could. We can improve on it by many orders of magnitude. And how do we do that? Well, the Tianji chip and others like it essentially rely on SRAM, a type of semiconductor memory for storing the data in the system. And SRAM is actually very costly in terms of size and power. And so there's another type of memory that one can use, which is called, well, memristors or various sorts of other types of ideas. But one can build a memory using tunable resistors. So this memory actually stores not bits, but numbers, real numbers, as a conductance value in the system. And it turns out that you can actually perform computation inside the memory. So that you save a huge amount of time and energy by doing in-memory computation, because you're not moving data around back and forth between a processor and a memory. It's highly parallel. In one step, you can perform a complete matrix vector multiplication. One time step. What happens is you essentially put voltages on the rows. Each of those voltages times a conductance is a multiplication. So that's Ohm's law. And then you collect the currents down the columns, and that's summing, and that's summation. So it's a MAC or a multiply add system. But the issue is that it can be done in one time step. One thing that I've just actually recently realized is this is logically and physically reversible. You can actually build something like this and have it be extremely low power. The way you do that is you actually use capacitive junctions instead of resistive junctions. And so when you perform a computation, instead of having to put power in and change things and look at power out, if you have a capacitive system, you essentially just have a bunch of charges in here. You put your input vector, a set of voltages on the input, and all you do is move the charges around in the system. So you never actually lose the charge. You don't dump it out. You can also run the system backwards. So it's reversible, and you're not discarding any of your intermediate computations. So in principle, you can do these computations with ridiculously low amounts of power. And then there's a bunch of other issues here. It turns out that even very crude devices today are already outperforming digital circuits like graphical processing units and the tensor processing units by factors of 100 in both speed and time. And this technology is primitive compared to what the CMOS that are used in that. So this is something that's just really it's really starting to take off. And it was just all over the place at this conference in China. There were dozens of groups working on it. However, my former group at Hewlett-Packard Enterprise has done something pretty cool recently, and that is they've shown that you can do very nonlinear types of calculations by taking a dot product engine and actually doing it recursively or doing it iteratively. So you essentially can take the output from a dot product engine, push it into the input, and essentially change a set of values on a vector, and essentially iterate to a solution. This hot field network, it's known to be essentially an energy minimization problem. Now the problem, the difficulty with energy minimization is when you have a very rugged or very steep energy landscape, there will be a global minimum out here. That's the answer to your problem. But then there will be many local minima. And so normally when people are trying to do a computation like this, they get stuck at a local minimum. So what my former employees at Hewlett-Packard did was they figured out how to actually use the noise inherent in the crossbar itself in order to perform what in computing would be a simulated annealing, but this is a real annealing process. So they can literally anneal the system to find the lowest energy state of the problem. And so they demonstrated this using something called MaxCut, which if you know what it is, great. If you don't, well, I'm not going to try to explain it because it would take the rest of my talk. But MaxCut is an NP-hard problem. In other words, the normal number of trivial steps that you'd have to do to solve the problem would go as something like 2 to the 60th power, since it's a 16-node problem, or it'd take something like 10 to the 18 steps to actually solve the problem if you did everything serially and didn't do parallelism. The thing to look at here is that when they started trying to tune things up and tweak things up, they were actually solving this 60-node MaxCut problem in 5 steps. Okay? So go from 10 to the 18 to 5. That's a pretty good improvement. Okay? Now, there's all sorts of issues with this, but the fact is that you can run this problem many, many times on a system like this in order to get some statistics and understand whether you've actually hit the lowest, the best value or not. Now, why did my colleagues at Hewlett-Packard choose MaxCut? Well, this is because this company called D-Wave came out with their quantum computer, and they actually chose MaxCut as an example to show how great the D-Wave quantum computer was in solving the problem. And so they chose the MaxCut problem. All right? So without getting into too much detail, what I'm going to just show you here is that this simple room temperature chip, really, that's really very crude. It's still sort of a lot of it's hand wired up, was able to perform, in terms of number of solutions per second per watt, 4 times 10 to the 6th solutions of this problem. D-Wave was 4 times 10 to minus 9. So this hot field network outperformed D-Wave by 15 orders of magnitude. 15 orders of magnitude. Room temperature, crude, high, something that can be dramatically improved upon. Okay? This probably cost a couple of bucks. About 100 million. Okay? So.
A lot of recent news on that, too.
Yes.
We won't talk about it, about quantum supremacy. Maybe during the Q&A later we'll talk about it.
Well, what I'll say is, I can flip a coin 53 times in 200 seconds, and so if Google has quantum supremacy, I've got Google supremacy. Okay?
All right, good.
So, to realize, now here I was asked to go out on a limb. So this is the first time I've said this number. I'm going out on a limb. I haven't proven it yet, but I believe that there are potentially 20 orders of magnitude improvement possible in these systems when I take all of the various things that I see and put them together and try to look at building a system. So this is not proven. They told me be bold, so I'm being bold. 20 orders of magnitude improvement that we could achieve over the next 10 years. So instead of Moore's law or Moore's scaling giving us a factor of 2 every year or so, what I'm saying here is we could get 1 to 2 orders of magnitude improvement every year. All right? But, it doesn't come for free. There's a lot of research and development that's going to be required. We got to sort of get up and start running. That's why I went to Texas A&M. I have a better chance of doing it there, I think, than in a company. I don't have to be proving to my bosses every 3 months that we're putting products in the market line that are helping out. So I'm trying to look at this 10-year timeline.
So your floor is the thermal limit? Is that your floor?
No,
Make that statement?
we can beat the thermal limit.
Talk.
We can beat the thermal limit. Okay, because I just told you, we can do it reversibly. So we can beat the thermal limit. And so there's a lot of issues here. It's a good question. There's a lot of issues here. Look, I'm not trying to compute a number to a huge precision. I'm looking at a probability. And how many significant figures do you need in a probability? Okay, so I don't need, so that's the issue. So areas of investigation. So what I'm trying to do is I'm trying to set up a research center in which we are looking at fundamental issues of computation. Essentially, going back and looking at a lot of great mathematics that's been done over the past, 30 years, and actually trying to recast it in terms that real human beings can understand. I think this is the major thing here, nonlinear dynamical circuit theory. This is the one thing that I think that people have just been ignoring and trying to sweep under the carpet for a very long time. Brains are nonlinear dynamical systems. We need to understand what that means in order to be able to harness these nonlinear dynamics in our actual systems. There's the devices that will actually represent this nonlinear dynamics. Okay, they are, one type of device is something that you may have heard of, and that's a memristor. But there are mem capacitors. There's other types of devices that fit into this nonlinear dynamical category. And so we need to be able to figure out those devices better. And I built up a system at Texas A&M to essentially be able to analyze these things. And then there's still, basic material science. I mean, how many people know that the very first integrated circuit was made out of germanium? I mean, even 10 years after the first transistor was made, people were still making their transistors out of germanium. The move from germanium to silicon was a big thing, and that's what enabled the larger integrated circuits to come along. So this field is still in a very, very early stage. So we still haven't figured out exactly what materials to use, and so that's going to actually be an important issue. Okay, so I'm just going to flip through some of these basic ideas here. Nonlinear dynamics, local activity, edge of chaos. These are all very important terms. These, yes?
I'll give you one here at 25.
Okay.
So you can use all 30 and you can use a little more if you want, but we have 10 minutes for questions today.
Yes.
So you're at 25.
Okay. So I think I'm going to be able to get it done in 5 minutes. So the nonlinear dynamics, it turns out that this theory was worked out in the 1960s. So there's a complete theory of nonlinear dynamical systems that was worked out in the 1960s, but nobody's ever used it, or hardly ever. Mainly because A, it's very hard, and B, it frankly wasn't communicated very well. We were talking about communications. But the person who developed this is now, there are other places around who have figured this out, so now there's now a CHUA, named after Leon CHUA. There's a CHUA memristor center at the Technical University of Dresden in Germany. And there's now, actually in 2 weeks, there's going to be inaugurated a CHUA memristor institute at the Huazhong University of Sciences and Technology in China. I mean, Leon was at Berkeley for most of his career. There's not a CHUA institute at Berkeley because nobody understands what he did there. Okay, so here's Leon. We film a 12-part lecture series, and so if you want to see what's going on, you can take a look at that. But the top of the line is that linearize and analyze is not valid for understanding nano devices or neurons. Those types of devices have become what I call pathologically nonlinear. And so any attempt to analyze them by first linearizing them is guaranteed to fail. It won't work. And in fact, that's the problem that a lot of people are having with their devices. They're following a procedure that's guaranteed to fail. So if you're gonna play in this game, you've got to actually confront the difficulties right up front. Okay? So, reestablish links between modern neurophysiology and computing. I mean, Todd was the one that started beating on people to look at spiking, but there's a lot of other cool things that have been going on in neurophysiology. One is spikes. I mean, the current dogma is that spikes are flying bits, and that information is transmitted by rate coding. Well, it turns out that there's been some recent research that essentially shows that spikes' shape actually matters. So a spike is not a flying bit, it's a packet of information. And so you obviously can convey a lot more information in a packet than you can in a single bit. All right? So we've been discounting the amount of computation or the amount of communication that brains are capable of. And the other issue is that individual synapses actually store more than one number. They store an entire, they really store a
Surface.
well, yeah. I mean, what they're doing is they're storing a tensor. All right. And so what you can think of is that when two spikes, if you want to call them that, collide in a neuron, what's actually happening is not just some simple multiplication factor that's going on. You're actually getting an outer product of essentially two multiple or multi-dimensional systems. Right? So actually, brains I think are a lot smarter than we ever thought they were. Or if this actually isn't right, I don't care. I think it's such a cool idea that this is what I want to build anyway. Right? There's no reason why we have to be constrained by exactly what the brain does. So that's an issue. Nonlinear device physics. So I've been working with a lot of groups. I've got a bunch of former postdocs out there now. I've got something like 30 postdocs that are that I've infected the world with. So I'm working with them. And so here's some issues where we've been actually using silver in silicon dioxide to emulate the calcium diffusive dynamics at synapses. And by looking at something like this, you can actually see that there's a shape to the spike, or that there's in this case, there's a potential to have essentially a tensorial synapse in the system. Here's something that we built recently. It's a neural network built entirely of memristors, no transistors at all. So everything is done in this network with memristors. Okay. Where does the gain come from? Well, it turns out that if you have the right type of memristor, you get gain. Okay? So you can do signal, you can do thresholding, logic, gain, using these two-dimensional devices. And that's how the brain does it. Neurons are effectively a two-terminal-like device, but a single neuron has memory, logic, and transmission all in one unit. So that's what we're trying to emulate here, using nothing but memristors. And here's another paper that, from another one of my former postdocs, in which he looked at something using vanadium dioxide, in which he was able to with very high fidelity reproduce the behavior of 23 out of 26 known biological types of representations that you find in the brain. Material science, well, there's just a ton of materials that can be done. I mean, this is a huge area. But just recently, and Paul will resonate with this, after working very hard about 15 years ago to kill the field of molecular electronics, now all of a sudden I've become a believer again. There's a new set of molecular materials out there that are actually vastly superior to any of the oxide materials that I've been studying for the past 15 years. In terms of every metric that you can think of, these things dramatically outperform. And in principle, you can actually get an improvement just by changing material if you could do it. That's not exactly known yet, but you'd get a 4 order magnitude efficiency improvement just by replacing a bunch of oxides that we're currently using today with this molecular system. All right, so here's my conclusions. I'm trying to look at brain-inspired architectures and computational models. And that involves essentially looking at new types of dynamical devices, things that are actually operating temporally, and supporting materials that have the fundamental features of these dynamics built into the material, rather than having to create it by somehow putting a bunch of smaller devices together. So when I talk about replacing 1,000 transistors with a single device, this is what I'm trying to do. I'm trying to go down to the properties of the basic material itself, find out what computation that material can do, then make a device out of it that can actually perform some very significant issue. This has the potential, I believe, I haven't proven it yet, but I'm working on that, to improve higher order neural networks. Not, this wouldn't translate to absolutely everything, but for a very high order neural network, such as a hot field network or a Bayesian net, I think we can improve by 10 to 20 orders of magnitude in terms of the power efficiency compared to what you can do with the best possible scaled or digital CMOS that you can think of, right? And the way you do this is by you beat the problem by having a very, very large number of very inexpensive devices. Each device, which can essentially perform what would take a very large number of transistors to do. So this will enable a very high order, a level of intelligence to be deployed at all scales. Everything like Tianji, all right, something that's going to sit right out at the edge of the internet, connected to a simple sensor where you're collecting data, but you want to do a lot of the analysis right there, and you don't want to have to actually transmit all of the data upstream, to a cloud scale data center. Same technology from beginning to end. And then essentially, if you want something to calculate something at very high precision, well, then you have the appropriate systems to do that. So, but what I'll say is that the competition in this area is already fierce. I mean, everything that I've told you today is actually well known by my colleagues and competitors in China, and so they're already down the road. And just like Tianji on the bicycle, it's going down the path. These guys are there's a lot of groups. They're very well funded, and they're going like gangbusters. So thank you very much.
Thank you. Thank you very much, Stan. The way we're going to run this is we're going to have a brief question and answer session after each speaker, and then a more extended one at the end when we're talking about things, common themes, things like that. So we'll start with the question. I have lots of questions, but I don't want to hog it, so please, from the audience first.
Let me ask a naive question, provably naive question. The current state of affairs of the Chinese projecting that they want to own 70 to 90% of the commercial chip market is really a commercial global competition issue.
Yes.
The current advantage that is touted to be owned by the U.S. is in the expertise to manufacture very high-end strategically important chips. What I'm getting is the implication from what you're saying is that if you've got your 20 orders of magnitude, at least initially, requires a level of manufacturing expertise that is not very high.
That is correct. You can do this with 20 nanometer fabrication capability and significantly outperform, say, 7 or 5 nanometer CMOS.
And that levels the playing field.
Yes.
Good comment. So let me. I can't resist but making a historical comment. I guess once you get gray hair, you always make historical comments. So I'm fascinated by what you're essentially doing is you're capturing the nonlinear dynamics by going to an analog engine.
Yes.
Looking to an analog engine.
That's correct.
Because you can't do that digitally. It's too freaking hard.
That is
if you
correct.
linearize, you lose what you're trying to simulate.
Yeah.
Very interesting historically, because we went digital in the first place to save energy, right? When the FET came out, I'm almost giving a lecture. I should maybe be an academic or something. But now we're at a point where, oh my God, how do you get more energy and savings? And it's going back to where we started, which was analog. I'm fascinated. We should call your talk Back to the Future.
Well, the issue here is that as has been understood now for quite some time because of Rolf Landauer and others. Computational cost at the baseline computational cost comes when you throw away intermediate results. You're increasing the entropy of the universe when you do that. Using a dot product engine, you never throw anything away. You have your data there. You perform all your computation in situ in one step in analog, and your data isn't changed. So and you can run the system backwards. So there's no effectively thermodynamic cost. And because if you really want to do this thing very efficiently, you can push this thing to as far reversible as you want to go. You can beat the thermal limit by just going reversible. And as I said, at the end of the day, what you're looking for is a probability. And how many significant figures do you want a probability to anyway? So you don't need. So what you're able to do is you're just able to strip whole bunch of stuff out of the system that you actually don't need to do in order to perform the computation that you actually want to do.
More questions? Yes, Paul.
Stan, very good. Thank you very much. Excellent talk. I'd be curious to your comments on the roadmap for the materials and devices end of things. What level of temporal and spatial stability do you need, or can you program around it, and how do you get to the level you need?
Well, as you know, I spent a lot of time worrying about defects and defect tolerance and all of that stuff. And so the crossbar structure has a tremendous amount of defect tolerance associated with it that you can essentially cheat and program around anything in the system. But in fact, we and others have already demonstrated as many as 10 to the 12th switching functions in oxide materials, and these molecular materials seem to go way beyond that. And the fact is that for the types of computation that I'm looking at, you actually rarely ever switch the materials. And so, if you actually want to store the data in a memory, you may just only write once, and then just use that memory as the substrate for doing the computation. So, in fact, I think that in terms of endurance and stability, we have far more than we actually need for this type of computation. But the fact is that the materials are being improved all the time. It's getting better and better because people are still pushing on trying to use these materials for memory. So the memory application is driving the quality and the capability for manufacturing this. And we can essentially take 3 or 4 steps back and say, look, whatever you've got that's in the cheapest fab that I can go, I'll use that.
Yeah, it's what I take away from this at the high level is there are scientifically sound reasons for believing there's many orders of magnitude of progress that are still awaiting us. So that it's not gloom and doom, right? This is just a change.
Mm-hmm. And so, one thing that Moore's law was this incredible period of time when our computational capability was increasing by roughly a factor of 2 every year. And when Moore's scaling really started to peter out, I got very depressed because I thought, we've got to keep things going exponentially. Well, now all of a sudden, I'm actually really believing that we can improve things by 1 to 2 orders of magnitude per year over a 10-year time frame.
I'd like to see that roadmap on my desk. That would be great.
Let's put it this way, I'm working on it.
That'd be good.
I'm not there yet, but it's
So I want to stay on time, but for a final question before we move on to try to stay on time. We will have time to talk at the end, so we want to make sure we have time to talk at the end. So yes, one final question before we move on.
So it also seems like this architecture really is helpful when you're essentially putting a lymph node system in, because you could go and check for homeostasis and find out whether 737 Max is actually, the sensors are actually performing properly.
Yes. This is, you make an extremely important point. These higher level neural networks are actually far better than a deep learning type of neural network because every number corresponds to a known physical thing or action.
Right.
So you can trace exactly a cause of events.
So actuaries are actually bookies for the insurance company, but what you can do is you can do a risk management system now essentially on their own.
Yes. Mm-hmm. Yes, that's exactly right.
Great. Well, thank you very much, Stan, and we're looking forward to the conversation afterwards. So I'd like to move on to introduce the next speaker, Dr. Todd Milton from the University of San Diego. We have a connection. I guess we were both DARPA alumni at the same time. I had the pleasure to sit on the source selection panel. I don't know if you probably remember that, Todd, of the Synapse program, which was pretty cool because I was a CMOS guy, but here's somebody trying to use CMOS to do like neurally inspired stuff. And since I had actually met John Hopfield when I was at Bell Labs as a very young scientist, I was really enamored of that. So that was a great program and some great stuff that came out of it. Todd's working on robotics in the EE department at the University of San Diego. And it was also with the Brain, right? The company was called the Brain. Brain Corporation. Brain Corporation, as probably spinning out some of the DARPA work. And also, as we said, it was at DARPA working on really realizing neurally inspired
architectures in, I guess primarily in CMOS kind of platforms, things that really work, chips that really work. So I've also heard some really interesting lectures on the future of computing and the evolution of computing systems that Todd has given publicly. So I'm really intrigued to hear his perspectives on the future of computing. So with that, Todd.
That's what this was about. So
Good.
just one small correction. The University of San Diego is a fine institution. I'm from the University of California, San Diego.
Okay.
But it is confusing. So I'm going to talk about what I call thermodynamic computing today. So this is a different vision where we get back to some of the basic questions in computing that I think we sort of lack foundation. Okay, so here's the outline for the talk. I'm going to do a little bit about motivation, why should you care, a little bit about thermodynamics. I'll talk about a vision for thermodynamic computing briefly. If I have time, I'll at a very summary level present the thermodynamic neural network idea that I developed, and then a few conclusions. Okay, motivation. A few observations. So computing absorbs 5% of US electrical power production today. Next generation semiconductor fabs are projected to cost $20 billion. Moore's law is on its last legs. Electron devices are comparable to the size of biological molecules, and for that reason thermodynamic fluctuations are a challenge. Paradoxically, however, while we avoid fluctuations in hardware, we are creating them in software to sample probability distributions in machine learning systems. But we are still about 1,000x above what people generally refer to as the Landauer limit of thermodynamic efficiency. Our computing systems possess far more computational potential than we will ever be able to program. And we are many orders of magnitude less capable and less efficient than brains, as Stan just mentioned. So my conclusion here is that we are in the late stages of a mature technology paradigm, but we're still a long way from fundamental limits. So a few more thoughts. I think that the primary problem in computing today is that the computers cannot organize themselves, that we have to basically program everything that they do in gruesome detail. And so we end up with these very large systems with trillions of degrees of freedom, but mostly they're doing the same few things over and over again. So the machines are ill-suited to evolving complex real-world problems. And I think the reason for this is that while the machines can transform information and energy into different sorts of things that we care about, they are literally frozen. They are too cold, and for that reason, they can't evolve on their own. Lastly, I'll comment, machine learning systems universally employ thermodynamic concepts, but they are still ad hoc solutions without an overarching physical paradigm to guide them. Okay, so here's the way I view the technology landscape. I got it divided up into 4 boxes: things that are programmed versus things that learn or horizontal, things that are dynamic online in the real world, things that are static or offline in the virtual world. And as a young man, everything was down here. Had a desktop computer. It was all entirely programmed. It was all static. It was all offline. Now, in the last couple decades, 2 things happened. We built computers. We were able to take them into the real world, but they're still almost entirely programmed. These are the things that sit in our pockets. We also built gigantic data centers, which is where we do the most of the machine learning stuff today is done there, but it's not in the real world. Okay, it does learn, but it's not in the real world. It's mostly offline data sets. We're fitting benchmarks and so forth. So where we want to be is up here. This is where the buzz is in all the tech press. This is where people think the future is. So we want our systems to be dynamic online in the real world, and they're going to have to learn because the real world's too complicated to program it all, or to train it all, frankly. Okay, so that's where we want to be. But conceptually, if I guessed, okay, what are the basic ideas that underline these various domains? So in these 3 domains, where I say we already have existing products and technologies, we do have the fundamental pieces in place. We more or less know how to describe what it is we're going to do on the computer. But we don't have that same understanding here. Okay? I think what we need here is what I call dynamic learning and inference. The ideas that I'm interested in come from non-equilibrium thermodynamics mostly. They're multi-scale quantum thermodynamic systems. It's a bunch of complicated stuff, but we don't have neat little descriptions of how it works yet. We have a bunch of ideas, but nothing that's sort of foundational that you can build a technology on yet. What we do today in this space, this is robotic space, is we mostly take ideas from here to here, and we try to bolt them together here, and we struggle massively because the world is always changing here, and we don't really know how to do that. So I'm going to talk about thermodynamic computing. It's grounded in a few hypotheses that I'm going to try to outline here before I go further. The first is, why thermodynamics? Why should you care about thermodynamics? So a few reasons. Thermodynamics is universal. It's the only field that we know that applies to everything without exception. It is the primary concern. I don't care what you're talking about. Cars, spaceships, computers, chairs, it's all thermodynamics. That's the most fundamental thing. Thermodynamics is temporal. The second law of thermodynamics is the only reason we know that anything should ever change. It's the only one. Thermodynamics is efficient, and by this I mean that when I look at natural systems and even human technologies, they are constantly evolving towards greater thermodynamic efficiency, or they fail. And I think the only reason that can happen is that it's thermodynamics that's at the bottom of things that's making it happen. And lastly, I'll say thermodynamics is not mechanistic, cannot be described using the ideas that we have today that we use to describe computers, for example. Can't describe the second law of thermodynamics as a mechanistic system. So my hypothesis is that thermodynamics drives the evolution of everything, that thermodynamic evolution is the missing unifying concept in computing, and probably in many other domains as well, and that the challenges in the current computing paradigm are fundamentally thermodynamic. Excuse me. In other words, too much power, fluctuations, enormous costs, inability to evolve in the real world, these are all thermodynamic issues. Lastly, I think that electronic systems, the ones that we build today, should be, in principle, extraordinarily well suited to thermodynamic evolution, but we don't let them do it. And so I think that thermodynamics should be the principal concept of future computing systems. So a little bit about thermodynamics. So if you took thermodynamics as I did, you learned that if you took an isolated system, this is this box here, and there's stuff inside that's ordered, that's this blue square, and stuff that's maybe disordered, what happens over time is that the thing becomes more disordered. So the ordered stuff melts or becomes gas or something like that. And the entropy of the system increases. This is thermodynamics as we mostly understand it today. However, this is nothing like the real world. This exists only in the mind of physicists. There are no real world systems that look like this. And in the real world, every system is open, and what we constantly see is that when we add free energy and raw materials and we eject work, heat, and other wastes, we get organization. Okay? In the real world, organizations are constantly coming into existence and out of existence. They don't violate the second law of thermodynamics because they're able to create entropy in the larger environment, but they do spontaneously create structure. This is what we see. This is not what we see. Okay. So the hypothesis here is that organizations evolve by relieving thermodynamic potentials and creating thermodynamic entropy in the larger environment. So here's an example. Thermodynamics of a tree. Okay, so with a tree, there's a thermodynamic potential between the water and the minerals in the ground and the carbon dioxide and the sunlight that's in the air. Okay? And what happens is a tree is an organization that spontaneously has emerged in order to connect these sources of potential and create entropy in the larger environment. What it does is it takes a bunch of high energy photons, turns them into a bunch of low energy photons, among other things. But you see this everywhere. A few more examples. A river is a structure that's spontaneously formed to relieve gravitational potential, makes the water go downhill easily. Lightning bolts, funnel clouds are because of thermodynamic potential differences in the atmosphere and on the ground. You boil water, you get bubbles that spontaneously form at the heated surface, an organization that did not previously exist, in order to transport heat to the unheated surface, to the atmospheric surface. Okay? So organizations are spontaneously forming all the time. The last comment is that, if you looked at these hydrothermal vents, you'll find out there's a whole ecosystem of stuff living down the bottom of the ocean where nothing should be alive. And at the bottom of this food chain is a bunch of chemicals coming out of the ground. And there's bacteria that eat those chemicals, and everything else eats the bacteria. The point that I'm trying to make here is that living things derive their existence from stuff that's not alive. And if you looked at the ecosystem as a whole, that's obviously true. Okay, we come from things that are not alive, and so the things that govern us as living things probably have a lot to do with what governs the things that are not living, which is usually where we think about thermodynamics. All right. Recently, 20 years ago anyway, there were some new ideas in non-equilibrium thermodynamics. This is known as the Jarzynski equality. It replaces the second law of inequality, work has to be greater than the change in the free energy, with an equality for open systems. Okay, you go, oh, okay, suddenly I go from an inequality to an equality. And so there's been kind of a little industry of people working in this space for the last 20 years. And as an example, Crookes has a more detailed theorem, a non-equilibrium fluctuation theorem. And what it says is that if you took a reaction this is an open thermodynamic system, it's driven by external potentials. If you average over a reaction in one direction and divided it by the same reaction going in the other direction, you average all of those things, you would end up with some measure of the amount of heat that's dumped into the environment. And again, it's an equality. Okay, so this is an advance in our thinking about thermodynamics. Yeah. This is another sort of similar idea which says that if a system is constantly driven externally and is relaxing to equilibrium along the way, that as it gets better and better at predicting what its next input is going to be, it becomes more and more thermodynamically efficient. And it comes right out of these fluctuation theorems. So what it says basically is that a system that's thermodynamically efficient is one that can predict what's going to be, what its inputs are going to be. It's one that's organized, so to create those predictions, and I contend that it gets this way through some kind of thermodynamic evolution, which this theory cannot yet explain. All right, so intuitively, what am I talking about? What did I do with the water? Did I have some water? There we go. So here's my intuitive interpretation of non-equilibrium fluctuation theorems. What it says is that when you're dissipating a lot of energy, you're basically a novice. You don't know what you're doing. Okay? There's a lot of energy loss. There's a lot of things being tried. There's a lot of adaptation and learning in the process of doing so. When you do know what you're doing, you're in the low dissipation condition, and you're the expert. You're efficient. It looks like it's effortless, right? And the thermodynamic evolution, you're able to predict what's going to happen. And there's an evolution that goes on in getting from here to here, all right? This is basically what those fluctuation theorems are saying in an intuitive way. So now I'm going to skip forward a little bit and talk about a vision for what we could do in computing with some of these ideas. The first thing I want to say, like Stan said, is that there is a long history of thermodynamics in computing, but we seem to be unaware of that fact currently, okay? Go back 200 years and look at major breakthroughs in thermodynamics and computing. They often came from the leading scientists of their time, and they were in both fields. Okay? And I contend that this lineage continues even today. Okay? And in fact, we're at a boundary where there's going to be some breakthroughs, just as these were breakthroughs in the past.
You're missing Kirkovich.
Okay, tell me later. I'm missing probably a ton of people, but yes. So I wanted to say a little bit about where I think thermodynamic computing fits with respect to quantum computing and classical computing. Okay? Classical computing is what we do now. And I'm going to do it in terms of fluctuations, thermodynamic fluctuation scales. Okay, so I've got temporal fluctuations on this axis, spatial fluctuations on this axis. I put a marker here to say, if I just set room temperature equal to the free electron energy, this is the scale that I'm talking about. Okay? It's a physics argument. Now what happens in classical systems is that the fluctuations are small compared to the things that we think about. Okay? So if you're a transistor, there's a lot of fluctuations going on inside, but in general, we don't care about them because they average out in some way. Okay? So in the classical domain, things are scale separated. I don't have to think about what's going on at the microscopic scale or at the fluctuation scale because things are big. And this also makes them mechanistic. We can think about them as machines in this space. Now in the quantum domain, basically you don't want any fluctuations. You want the fluctuations to be large compared to the scale of the system that you care about. And when this happens, you get these coherent sort of single scale quantum effects, all this magic stuff, you know, that the press likes to talk about. But it basically means that fluctuations don't matter. They don't matter here because we average them out, and they don't matter here because there aren't any. Okay? Now in both cases, in both the classical domain and the quantum domain, the problem is that we want to operate right on this boundary right now. Okay? The quantum guys are desperately trying to get bigger systems, lower temperatures, right, and still maintain a single scale. And in the classical domain, we keep wanting to make things smaller, so we keep getting into trouble. The thermodynamic domain is right in the middle. Okay? It's the domain where you can't separate scales and you can't ignore fluctuations. This is the domain where your brain works, where every living system operates, where cells work. This is where the world really is. So when we pretend that we're going to do things like this, we unfortunately ignore the fact that we're actually trying to do it over here. And so it isn't going to work, in my opinion. Okay? So as a further comment here, if you look at sort of things that we're familiar with today, in the quantum domain, the fluctuations are large if you're an atom or a small molecule. So they look like a unit, right? A quantum unit. Transistors, gates, things that we usually think about in computing domains are large compared to the fluctuation scales, so they look like devices, right? We can abstract them. We don't have to worry about all this stuff going on. We can describe them as state machines and a bunch of other simplifications. But here, the domain of large molecules and nanotechnology is fundamentally thermodynamic, and this is where living systems are. Okay, so a comment about living systems versus modern electronic systems, all right? So in living systems, we've got mostly chemical potentials that are driving things. In electronics, we have mostly electrical potentials that are driving things. Interesting thing is that the energy scales and the size scales are roughly the same now. Because of the advances in electronics, voltage is going down, size is going down. The energy and size scales are roughly the same for electronic systems and living systems. And the reason for that is that they both derive from the electronic structure of the materials of which they're composed. And I contend that our electronic systems today do not evolve because we are killing ourselves to make sure that they don't. The advantage of making sure that they don't evolve is that they do exactly what we tell them to do, over and over and over again, which can be of great value in many domains. But I think it becomes very limiting if you want a system that's able to take on the real world by itself. Okay, system concept for a thermodynamic computer. This is sort of the way a conventional classical computer looks like. You got a data, you got a program, you got some computer in the middle, you got output, you got some feedback. Okay? The point I want to make here is that at all the interfaces to the systems today, there's a person. Okay? There's a person who is the interface that decides what data goes in, who decides what the program is, who decides whether the output is valuable in the world or not. Okay? So the human is the interface to the world, and the computer is a box. Without us, the computers don't do anything, and they're useless, in fact. Now, a thermodynamic computer I think of as a different sort of animal in which it is connected directly to energetic potentials in the environment. You can think of them as electrical or information potentials, if you like, because I think that's a natural way for us to think about it. They're also connected to a thermal reservoir from which they derive their fluctuations. And this is a fundamental piece. This is just not, it's not just a place where you dump heat. You do dump heat, but it's also a place where fluctuations spontaneously enter the system.
Semi-permeable membrane.
What?
Semi-permeable membranes.
Maybe. Well, hang on to that thought. What I imagine we should do here is that we should be able to take, with a conventional computer, place some constraints on this thermodynamic computer so that it does things that we care about, but then let it figure out all the details. Okay? That's the basic idea. I mean, this is not unlike any other hybrid computing system you would see today, except that this one, I contend, should be connected to the real world and evolve thermodynamic. So here's an idea. Here's the same idea again. I've got this thermodynamic computer here. It's connected to another computer that I'm not showing. It's connected to an environment in which there's information and there's electrical potentials and so forth. This thing, potentials come here, this thing creates potentials here, and there's a bunch of heat flowing in and out of a reservoir. Okay? Okay, so how does it work? Right? How should such a thing work? Why would it evolve a structure? Okay, so imagine this as a kind of thought exercise. I've got some number of cores, they're connected into a network somehow, okay? Maybe I can reconfigure the network, but what happens is that as energy flows through this system, it creates fluctuations where that energy is dissipated, okay? So if it's dissipating a lot of energy in one spot, it's going to get a lot of fluctuations. Now, if those fluctuations spontaneously fall into a state in which that dissipation decreases, then the fluctuations decrease and the system stabilizes. Does that make sense? So you create heat, you create fluctuations, you get a fluctuation that effectively transports energy, then that stabilizes the state on that fluctuation. And that this is the way a system would evolve thermodynamically. So here's a cartoon I made even when I was at DARPA. So imagine here's a network of cores again. I'm defining a problem, which is the environment of energy that it's connected to in some way. As a programmer, this is the computer that's on top. I can go in and set certain pieces of this thing up to be certain states or functions that I want them to be. I'm just going to say, do this. I'm the programmer. And then what happens is I turn it on, and it starts fluctuating different states for these different little cores, and as it becomes good at moving energy through itself, it stabilizes. Okay? And it solves the problem presented to it by the environment because it stabilizes in a low energy configuration. I'm going to skip this. We're out of time. Okay. Now, so in January of this year, there was a workshop in Hawaii. Stan and I were on the organizing committee, and so we wrote a report about what thermodynamic computing could be. It should come out next week. Okay? It was sponsored by the Computing Community Consortium. And you can see a bunch of ideas. We don't know how to do all this obviously yet. It outlines a bunch of research questions, research directions, the whole thing. Okay? Okay, now thermodynamic neural network. How much time have I got, Mike?
I would say about 5 minutes if you want to leave time for questions. So try to think about wrapping up if you want to have some discussion.
Let me be very quick then. Can you make this play? There should be a... Not going, is it? All right, let's skip it since... No luck? So if you'd been able to see this, what you would have seen was small metallic beads in a petri dish with oil in it, and electrodes at high potentials, one in the center of the petri dish and one on the ring around the edge. And when you turn the potential on, what happens is you get all these cool fluctuations of the balls moving around in the oil, and they form these beautiful tree-like structures until they connect the potential and basically are very efficient at moving the charge through from one electrode to the other electrode. And it sort of illustrates all of the ideas that I just told you, but in a very simple physical system. And this was something that was done under one of my DARPA projects. It was called Physical Intelligence, and it was the thing that inspired me to build this model. It's a neural network model. I was partially inspired by the Ising model, if you know that model. Let me back up for a second. Why do we need a model? We need a model system because the ideas, these thermodynamic ideas, these non-equilibrium thermodynamic ideas that I have, that I think are missing in computing, currently lack a simple illustration where you can look at it and see it and feel it, okay? So the goal of this model was to create that. I looked at a lot of current neural network models, like Ising models, perceptrons, hot field nets, Boltzmann machines. I couldn't make any of them do what I thought was the important thing to do. So I made up my own, okay? It is a neural network model. It's more complex. There's a paper on the archive. You can read this if you're really interested in it. But what it's set up to do is the nodes are thought of as being vehicles that conduct charge through themselves and update their weights in order to improve their charge conduction efficiency. That's all they do. And I introduced a bunch of physics. So I'll show you a bunch of examples in a second where I've got a bunch of nodes laid out in a rectangular grid connected with periodic boundary conditions. So you'll see a bunch of these in a second. And they can be connected to an environment that drives charge into them. And the goal of the network is to figure out how to move the charge from one potential to another complementary potential. Okay, so here are the conceptual highlights of the model. Charge is conserved. Most machine learning systems have no concept of a conservation law, but every physical system is full of conserved quantities. And if we don't get the conserved quantities into the models, they will not organize correctly. Problem with a computer is you can do anything you want. You can get rid of any garbage you want. But you can't do that in a real physical system. In a real physical system where you have enormous numbers of conserved quantities, if you want to get rid of something, you have to have a way of getting rid of it. You have to have an organization that permits it to happen. And it's that need to get rid of and move conserved quantities under the laws of thermodynamics that drives self-organization, I think. Okay, so in this model, there are positive and negative charges. They're conserved, and they don't cancel because there's no mechanism that allows them to cancel. That will require that I think of things differently in different compartments. The neurons will have 4 different kinds of compartments. Charge accumulates on node compartments, and it's that charge accumulation that creates the potentials that drive the organization and the charge through the network. In other words, if you have a conserved quantity, a thermodynamic potential is the result of imbalances in conserved quantities in the environment. If I have if I have positive charge here in a clump and negative charge here in a clump, I've got a potential that is only relieved by moving them and dispersing that accumulation of charge. All adaptation in the model is by Boltzmann statistics. It uses a combination of rapid, global, reversible relaxation of the node state, something that Stan also referred to, followed by slower, local, irreversible adaptation of the edge and compartment states. And this is the way you create multi-scale spatial temporal complexity in a self-organizing system like that. And it's easy to do. I'm going to skip this. I'm going to say, let me move on. Long-term memory is stored in the edge weights. Intermediate-term memory ends up being stored in the compartment charges. And short-term memory is stored in the node states. You do this correctly, you get 3 classes of memory that just fall out of the system. Okay? Nodes can be connected as networks of any type without creating dynamic instabilities. Node and edge updates are continuous online. There's no learning rates or decay rates. There's no backpropagation, and there's no top-down orchestration. The nodes are simply little units that talk to each other and follow all these physical laws. So lastly, the TNN unifies concepts of, these are the core physical concepts that I was struggling for many years to get into this model. Conservation, potentiation, fluctuation, dissipation, adaptation, and equilibration. Okay? Those 6 ideas are the things that are physically foundational to everything in the natural world that are more or less entirely ignored in computing systems today. Okay, so
I would wrap it to have
Yeah.
time for 2 questions.
okay, I'll wrap it. I was going to show you some cool multi-scale simulations, but I'll come back to it. Okay.
We'll have time. We'll have
Okay.
time at the end to make some more
Questions?
comments. So yes, thanks, Todd. So please, questions. All right. So then I'll take my prerogative. This is great. I love having the prerogative. So I understand the the concept of allowing fluctuations, right? You want to be in a regime where you have fluctuations.
Right.
So in order to be efficient, aren't you then, the goal then is to just use those fluctuations to find the optimum state, so then it will evolve into a state with little to no fluctuation. Do I have that right, or did I understand that right?
I think
If left to evolve,
I think the answer is it depends. You know, if you have a very strong potential driving the system, the goal is that the fluctuations will just drive the system into the lowest energy state. It's kind of a needle. Okay?
yeah, it reminds me a lot of the Hopfield landscape, right? The energy landscape, right? And you're adding pulses of energy to pop it out.
But there's nothing ad hoc in this model about where the fluctuations come from. Okay? It is, you have a Hamiltonian, you have a Boltzmann distribution, and that's it. Okay? There's no noise sources, there's no annealing schedules, there's none of this junk.
Do you have a finite temperature?
You have a finite temperature, which you can change, right? You can set, like in this example, I have different temperatures for the nodes and the edge states, but you know, there's a few knobs you can turn. Okay. Now, on the other hand, I think a natural system, say our brains, is always in a state of constant fluctuation, right? There's some method of preserving what it is we know while constantly fluctuating and exploring new spaces. This is how we think, I think, anyway. And this model can also do that. You can train it, and then you can let it fluctuate, and it can largely remember what it has been previously trained to do by potentials it's seen before. All right? So this is the plasticity stability problem, you know, that neural networks have never figured out. I claim the answer is that if you are working with conserved quantities and fundamental physical ideas, then those problems, you can see a solution to those problems that is a natural part of what you've done.
So let me make a generalization. You tell me if it's right or wrong. So what you're looking at, I'm trying to appeal to the broad concept, is self-evolving, right? Computation that's self-evolving using thermodynamics as the organizing principle.
Yes.
Right. There are other ways to imagine self-evolving, but that's the paradigm.
No, I disagree.
Or you say that
There are no other
related.
ways.
All right,
There are
okay,
no other
this
ways.
is good.
It is thermodynamic. I'm not the first person to say it. What I am saying, though, is that our thinking about computing is so contaminated by the way we do it today that we are missing the big pictures. The big
Frozen,
picture is
right?
the
We're
small
frozen
stuff.
into our old way of
We are stuck. We're completely stuck. Yeah,
Paul.
go ahead.
What would be the physical instantiation of this system, or what are some potential ones?
Well, like half of the stuff that Stan showed, right? If we could pull it together, I think with some conceptual foundations about what the basic pieces were that how they needed to go together, then we've got it. We can build all kinds of small electronic systems that have fluctuations, right? I don't know how we deal with all the conservation stuff yet. This model system is not something you would want to build directly in hardware. This is a conceptual thinking piece that could help you figure out what it is you would want your hardware to do, perhaps. Yeah.
Follow-up question.
Yeah.
As you see where we are right now, what's the next big milestone that needs to be reached for thermodynamic computing?
I would say there are a couple of things. We need to.
Do you have a comment on this one?
Yes.
Oh, I'm sorry. Is
Go
there a
ahead.
quick comment from the audience?
Yes, Russ Fang. Krukovich has come up with something called a thermon, called fifth force.
Okay.
And the bottom line is it's a scalar force, if you can if you can get with that. And it's completely thermodynamic and uses the idea of Einstein's troll to take away the garbage.
I don't know that one, so I'm happy to talk about that with you. I'm sorry. What do we need to do?
What's the next big milestone?
Okay, so that report has a gazillion ideas in it, but let me sort of boil it down for you, what I think we need to do. Okay, we need to extend the current non-equilibrium fluctuation dissipation theorems to include adaptation, which they don't currently have. I don't know how to do that. We need to build small-scale electronic self-organizing systems that don't solve any damn problem. Here's the problem in computing today. Gee, I would like to build a really generally capable, intelligent device. Okay, I think I know how to do that, and this is how I would build this thing. And the first question someone will ask me is, what's it good for? That's the wrong question. As soon as we insert ourselves into the process of figuring out how to make a general artificial intelligence, we will not build a general artificial intelligence. A general artificial intelligence must have an existence independent of us, or it will not be general in any sense. So there's a catch-22 in every single funding agency and every single project I've ever seen, which is, yeah, I'm going to build this fantastic, enormously capable intelligence, and what it's going to do is drive a car. And it's ridiculous. I mean, if we really want intelligence to drive a car, we ought to first have something that's at least as smart as a worm, right? And we don't have that because we can't get anybody to fund the development of the worm intelligence. I contend that we could take small-scale electronic systems, not too many devices, we could show all the basic physics, these ideas here, at small scale with the stuff that Stan is working on. And then we'd have an example of what it looks like at a small scale. And that's the right thing to do. And if we did that, then what we could do is we could develop the conceptual models and the engineering tools we would need to begin to scale those things. And we could learn how to constrain them so that they do things that we care about. So that, like, we train our dog not to pee on the rug, we train it to go outside. You know, we don't destroy the dog in the process of training it how to do that.
Good question on what the substrate is to test these ideas out on. But in order to stay on time, so I'd like to move to a 10-minute break before we continue. So 10-minute break.
Can that demo
Smoke them if you got it. Okay, if everybody can make their way back to their seats, we'll get started. We're pretty close to being on schedule, so I appreciate that. And we'll keep things rolling right along here. So thanks for your interest. I do want to emphasize, a couple of people have asked me before, that these proceedings will be available as a video link. And so that will increase your range of influence, right, with people. Absolutely. So lots of folks who are interested in this topic, deeply interested, just couldn't make it today, even though some had RSVP'd and then they were called away for other reasons. So that will be available. I'm sure they're going to get a lot out of this because my juices are flowing for sure. So this is pretty cool. I'd like to move to the next speaker, Bruce McLennan from the. I'm going to read this because I want to be university right. I don't want to make another mistake. University of Tennessee, Knoxville. He works in the Electrical Engineering and Computer Science Department, and his interest is bio-inspired computing. So this is something we've heard a little bit before, but we're looking at, we're interested to hear what Bruce's take on this is. The other thing that struck me about his bio was you actually have industry experience too. So he's a deep academic thinker, but also knows what can be done in the real world. I believe he worked for Intel, right? So that's a great combination of real world awareness with thinking of what's coming down the pipe. So with that, Bruce, the floor is yours.
Where's the, I see. What I'd like to talk today about is unconventional computation in the broad sense. I'm a computer scientist by training, and so I'm coming at things from a more formal perspective, not so much a hardware perspective, although I did have some experience at Intel in the late 1970s. And one of the interesting questions we got from the hardware and device engineers was, we can put so many thousand, in those days it was 1,000 transistors on a chip, what would you like them to do? And in the absence of some answer from us, they would just do another processor like the last one, which in this case was the 8080. This has always got me thinking about, okay, we have this technology, what can we do with it? This is based, I'm going to talk a little bit about unconventional computation as a broad concept and the importance of investigating unconventional computation, and then look at a little bit on what computation is in general, because I think this is the broad sort of view we need, is what, in a broad sense, is computation. It's not just digital sequential logic. And then I want to focus down a little bit on embodied computation, where we have computational systems interacting with the physical world, and then talk a little bit about some of my own recent research on morphogenetic engineering. So, what's unconventional computation? Well, it's computation, it's not conventional, it's a negative term. So, you know, think about whatever you know about conventional or ordinary computation in the ordinary sense. If you change one or more of those variables, you're doing unconventional computation. So here's just a few of the fairly obvious ones. I'm on an architecture, binary digital electronics, random access memory, stored programming, sequential execution, and so forth. So I think it's important from just a pure scientific standpoint to investigate all of these other avenues of computation. Stan showed this very nice slide of the history of brain-inspired computation. And I teach machine learning, and I'm often struck, and I point out to my students how many of the citations are to the early 1990s or 1980s. A lot of the capital we're running on now with machine learning and all of the technologies that are built on machine learning were developed in the 1980s, or the early 90s, or even before, back in the 70s and the 60s, and so forth. And so that's the lead time. We need to be exploring new ideas so that 20 years from now, they will be developed enough that they can be exploited the way we're exploiting machine learning now. So I think computer science, as a science, should be studying all of the manifestations of computing. And that includes computing in our devices, in our possible devices, in our brains, and in nature in general, because nature does a lot of computing. And we can learn new ways of computing by studying how nature does computing. And that's why I'm in particular interested in bio-inspired computing. Because many of the things that we find it difficult to do with our computers, even with our more contemporary machine learning technologies, nature solves these problems very well. And so, no, we don't have to ape nature. We don't have to do things the same way nature does it. But if nature does it much better than we can do it, then we should certainly pay attention to how these things work in nature. And then we can think about improving on them as well. End of Moore's law we all know about. But the way I look at this is there's lots of technological and even economic issues in terms of how far you can push Moore's law. But the fundamental problem is we're using physical processes to implement computing abstractions. And we have benefited from many levels of abstraction, from going from the atomic scale of matter up through our devices, up through our digital logic, and then up through computing abstraction. So I've shown here that in effect what we're doing is that we're going from systems, transistors fundamentally, that basically are obeying continuous differential equations, using them to simulate discrete systems, and then putting together lots of discrete components to simulate, again, sometimes continuous systems. So this has been very nice. The level of Boolean logic, which goes back to 1853, I believe, has been a nice stable level for design. We can implement Boolean logic in all sorts of different technologies, relays, vacuum tubes, discrete transistors, integrated circuits. It's the same Boolean logic. In turn, we can use this Boolean logic to implement all sorts of different computer architectures. Computer architectures have changed over the decades, but it's the same Boolean logic basically underneath it. That's been very valuable in terms of driving the computing industry, because essentially it decouples these two levels of how you implement the Boolean logic and what you do with the Boolean logic. Same with differences in time scale. We've gone from, again, low-level continuous processes, kind of twisted them around to look like discrete time processes, and then use them again to implement higher order abstractions. Does this thing have a pointer on it?
If it did, it wouldn't work anyway.
Oh, that's right. Okay, so what are the implications?
Thermodynamics.
What are the implications of this convergence? So the takeaway story for me is that the laws of physics are not going to change. So to get higher densities and higher speeds, we need to draw these two closer together. We need to have the physics and the computing abstractions closer together. Since the laws of physics are not going to change, that means that our computer abstractions have to become more like the laws of physics, broadly understood. So there's fewer levels of abstraction. So what this suggests is that we need to implement our computing abstractions more directly in terms of the laws of physics. Now, this is a very broad way of saying something that Stan certainly mentioned previously, was analog computation is very efficient. And in fact, I remember, it reminded me at the IEEE First International Conference on Neural Networks in 1987, Carver Mead got up, one of our great contributors to digital VLSI, and he said the future of electronics is analog VLSI. And that caught my attention. I think it caught a lot of people's attention. For this very fact that it takes lots and lots of components to do digital addition, but it only takes 4 transistors to do signed analog addition. So in terms of the number of components it requires to do stuff like arithmetic, like those multiplications and additions that you do for the dot products and the matrix vector multiplications, you can do it with many fewer transitions. And that's because you're working more directly with the laws of physics. You're adding things, quantities that add, physical quantities that add, for example, or multiply. So my takeaway for post-Moore's law of computing is that there'll be a greater assimilation of computation to physics. And so we have all of these physical processes we can think about exploiting for computation. So this then motivates us to think about what is computation in general. And I think I'll try and go through this fairly quickly. But partly it's just questioning our assumptions. So Rolf Landauer has been mentioned a couple times already with his famous slogan, information is physical. And so in the broad sense, information is represented by some sort of form or organization we're imposing on some generic substrate, a substrate of matter and energy. What we need to keep in mind is that the state space can be discrete, for instance, as it is in a digital computer, or it can be continuous, as it is in analog computation. What I've described here is the address space, the arrangement of the components. We can think either of discrete cells, like we have in a conventional digital computer, or a continuum of states. Other sorts of topological organization of information as well. And so these are new ways of thinking about computation that we're not so familiar with. Or they're old ways that we need to re-examine. People made analog computers. They were a very important tool for computation up into the middle of the 20th century. People used continuous representations of information in analog computing devices. Von Neumann Landauer limit has been mentioned, and again, this is we're not there yet, but I would say it's in sight. Reversible computing, as Stan mentioned, is one way around this problem. But reversible computing is not what we normally do, right? This is one reason quantum computing is so hard, is because it's reversible. And we use metaphors, and this goes back to the Turing machine, metaphors of blackboards, mathematicians writing on blackboards. You write stuff down, you erase it, you copy stuff. That's what our computer programs do, right? But erasing is what must dissipate a certain minimum amount of energy, according to the von Neumann Landauer bound. And so if we want to avoid this, we have to get away from this way of thinking about information as copying, erasing, moving stuff. Well, moving is okay. We can move it around with arbitrarily small amounts of information, but we can't do these other things. So this, again, is a new way of thinking about computing that we're not so good at. It doesn't agree so well with our macroscopic understanding of the world and just our everyday physical interaction with the world. Information processing also, the conventional computation proceeds in a series of discrete steps. Analog computing does not necessarily do that. Certainly, old physical analog computers often would compute in continuous time. Because essentially what they were doing was integrating differential equations. And so there's a lot of new work. Ising systems, for example, are example of this, and hot field networks that can operate in continuous time, and so forth. That basically then look at the different models of how information processing proceeds in time. Programmability. We tend to think of programs as being discrete texts of some sort, but this also does not have to be. So effectively a Hamiltonian or a potential surface, which is really a continuous representation of a program, is another way of thinking about programming a system. So these are we don't necessarily construct these continuous surfaces or energy functions by hand, but they might be a result of, for example, a machine learning process. Universality. In computer science, we tend to define universality as being able to program a system so that we can simulate any Turing machine. But this is based on a very specific notion of two machines being equivalent. Namely, they compute the same mathematical function, the same correspondence of inputs and outputs. That's not always such a useful concept of universality. And so I think, especially when we're dealing with unconventional computation, we have to think about what I call the frame of relevance of a model. Frame of relevance of a model is the sort of questions it's designed to ask and answer. So if you think of any model, a wind tunnel model, a mathematical model, any sort of model is designed to answer and ask and answer certain types of questions. And that applies also to the Turing machine model. And often those are not the questions we want to ask when we're looking at an unconventional computing paradigm. So again, one of the things I'm interested in is robotics. And so if you're interested in something that will control a robot body, you're especially interested in real-time response. Even if you're thinking about something like an AI system for an autonomous vehicle, real-time response is also important, but also that it make reasonable judgments about obstacles and things like that. So there's lots of different notions of universality. Logic gate universality is sometimes used basically if you can do ands and nots. You, in principle, could do anything that we do on a conventional digital computer. So let me move on then a bit to embodied computation, because this gets at some of these issues. So embodied computation is a term I use to specifically refer to computational aspects that are related to the notion of embodied artificial intelligence. There's been a lot of work that's been done in artificial intelligence and in cognitive science over recent decades, showing the importance of the body in cognition. And this, again, a lot of the capital we're running on in machine learning and in AI is based on neuroscience from the 1980s and before. And there's been a lot of progress in neuroscience since then. And part of that is understanding the important role that the body plays in cognition. Animals fundamentally are trying to control their physical bodies. And the nervous system is the way they do that. Animals move. That's why animals have nervous systems and plants don't. And so it's really important both in understanding how they do this. And one of the important points is that if you incorporate embodiment, you actually find that some computational problems are easier to solve. So for example, animals have very rich sensory input. If you think about all of the inputs from your muscle fibers, from your skin, obviously very, very high resolution sense organs like your eyes and your ears, that's very high dimensional input. And normally we think about the curse of dimension, that this is going to make all of these computational problems much harder. But in terms of neurophysiology, it actually makes many of them easier. And in particular, the fact that an organism is interacting with its environment, that it's out there moving around, it's actually conditioning the sensory input that it's getting. And that helps it to interpret that sensory input better. So it's the fact that the animal is controlling the body, getting this very rich input, and also able to influence its environment is part of what helps the nervous system have to do less work to, for example, interpret its sensory data. So effectively, some of the computation has been offloaded into the physical body. Another classic example is an animal doesn't have to calculate the exact trajectory of its swinging legs or arms, for example, because it has natural mechanical properties that do that automatically. So it needs to just do a bit of higher level control to govern that. So many problems are actually made simpler by making use of the fact that the cognitive part, the brain, if you like, and the nervous system is embodied in a body. So if we generalize these ideas to computation, I define embodied computation as computation in which either the physical realization of the computation or the physical effects of the computation are essential to that computation. So what that means is that the computation, if we're thinking of it as information processing, it's depending on the physical processes by which it's implemented. It's using some physical processes directly. And the physical effects is that often the output of the computation is not information, it's some sort of physical reorganization or physical action. So I think this is probably clear enough. We've seen some other examples of using physical systems directly to implement some sort of physical process. I'll show a couple examples here of my own. Diffusion is a process that occurs, of course, in really all fluids. And it's computationally very useful. There's lots of things you can use diffusion for. You can use it for path planning, you can use it for searching, you can use it for broadcasting information, you can use it for optimization, constraint satisfaction, and so forth. Diffusion is very expensive to simulate on a computer, but diffusion is a natural property in many physical systems. And so what we find in natural computation or computation in nature is that many organisms make use of diffusion as an information processing resource. Randomness, again, we've seen examples of this. So there's lots of uses for randomness in computation. But often this can comes for free, for instance, in the form of thermal noise or in forms of other sorts of unpredictable sorts of processes. Quantum phenomena is a really great example. I don't need to say too much about it right now, but this is certainly a case where we can directly exploit physical processes and get much more efficient processing than we might be able to without it. And again, I would, a lot of our quantum computing, we still think about qubits, right? There's a tendency to think of them like, they're two-state, they can be in superposition, but they're really two-state devices. But again, these are continuous, these systems have a continuous state space, right? And so they're really analog devices, you should think about them that way. Dynamical systems. So we can construct dynamical systems. This is just an abstract description of the system here in terms of some multipliers and adders and integrators. It's a continuous time dynamical system that satisfies the Boolean satisfiability problem and can be implemented electronically. So that's one cell out of a matrix. So again, this is a classic discrete optimization, discrete combinatorial optimization problem that can be solved by an endless time dynamical system. Fairly obvious idea that it's settling into an energy minimum. And you can see here there's a simple simulation of it here as the variables settle into their 0 or 1 states with some essentially changes of the decisions. So continuous time systems, but spatially continuous systems as well. We don't have to think about computational systems being made out of a bunch of discrete components connected together. There are many phenomena in nature described by partial differential equations. These are massively parallel. We can make use of them. And what I find particularly interesting is that the same basic mathematics that we use for describing some physical systems also describes much of the processing that takes place in cortical maps in the brain. Okay? So again, we can often lift the mathematics and then apply it in another system with a different physical realization. So this is perhaps the prime slogan of embodied computation and related ideas such as physical computation is respect the medium. That has not been so much what we have done with digital electronics, where we have, as some people describe it, we've tortured the medium of taking these basically continuous electrical processes and making them look like they are Boolean processes. So the other slogan is exploit the physics, don't circumvent it. So as much as possible, try and use the physical processes directly to implement computational processes. So now that's, there's lots of challenges, not the least of which is that these areas have not been explored very much. And so there's just a lot of research to be done, decades of research to be done. One of the reasons I do bio-inspired computing is we can often find examples of this in nature, and that can give us hints about how some of these systems can work. So that's one side. If we recognize that computational systems are physical systems, we can try and set up the physical processes to do the computation we want. But in the process of doing the computation, physical stuff happens. Matter and energy gets moved around, electrons if nothing else. And we can turn that around and say, okay, what if what we want to do is move around matter and energy? Can we use ideas from computing to organize that movement of matter and energy? So this is where we get into using computational ideas for their physical effect. And this, again, is something we see in nature because a lot of the information processing that goes on in nature is not to receive some answer. It's to behave or to govern some physical process within the organism or within the colony, for example. So within the organism's body or within its interactions with the environment, this comes back again to the idea of embodiment. And a lot of what goes on is to govern or to control the body of the organism and its interactions with its environment. In particular, these self-star properties are sometimes called, that we find so commonly in nature. Adaptation and evolution would be examples as well, are things where an organism is using computational processes to reorganize itself in some way or to repair itself. Okay, I'll say this. The trade-offs are different. You know, when we're doing computing, we want to move a little bit of stuff because that means low energy. When we're doing embodied computation for physical effect, we may want to move a lot of stuff. So,
think about wrapping up so we have some time for some questions.
okay, I'll try and just quickly show you this. So morphogenetic engineering. This is an attempt to apply some of these ideas to a specific problem. How do we create complex three-dimensional systems? And I'm thinking here, for example, robots with highly complex sensors, highly complex actuators, and some sort of brain-inspired nervous system of mammal-scale complexity. How do we put together something like that? So we need a robust system for assembling very complex systems. And so this is a nervous system, something like 6 or 7 orders of magnitude of structure. If we want a brain of comparable computational ability to a human brain or even a cat brain, we need to cover really all of these scales of complexity. So how do we wire up such a thing? So looking at it again from a computational standpoint, I'm looking in terms of microscopic agents. They could be micro robots. They could be cells, genetically engineered cells, essentially to act like microscopic robots, or in some cases even complex macromolecules that have computational properties. And then coordinating these to assemble complex structures. I'll skip this. I'll skip this. There's really about 15 fundamental processes that take place in embryological development. If we can do these, in principle, we could make something as complex as an animal body. So I've got this is trying to get away from crossbars. How do we wire up neurons without crossbars or something equivalent to a crossbar? Because that's n squared space, okay? So what I'm looking at here is how can we wire up something, again, with the complexity of a human or animal brain. So one example, because we want to coordinate very large numbers of agents, is to use flocking algorithms. I hope this video will play. How do I play it? There we go. So this is 5,000 simulated micro-robots, essentially wiring up connections between randomly chosen origins and destinations using the modified flocking algorithm. They're using an algorithm so they don't collide with other fibers that are already in there. So we want algorithms that will scale up to very large numbers, hundreds of thousands or millions. Okay? So we don't want something that's just going to work with 100 agents. We want very dense nerve fibers connecting different regions of our artificial brain. Here you'll see this is a collision. So we say if you want it to scale it up to infinity. So we take everything to the continuum state where we've got partial differential equations. So it's the same algorithm now, but basically controlling partial differential equations. And these are the simulated robot mass, I would say now, rather than swarm, laying down pathways from a source to a destination. And you can see they're following an attractant gradient to get there. So it's going to get there. I want to just skip ahead and say, how can we do more complex structures? Again, we're borrowing ideas from biology. So this is a chicken embryo. It generates a certain number of 33 is human. I forget how many you do for a chicken. Maybe it says here. But as it grows, it's sending out periodic pulses of a segmentation signal that's basically creating these spinal segments. And so if we want, chickens have 35. So if we want to create a structure like this, we can implement this same algorithm. And I'll just briefly show you this. So what we're doing here, this is the tail bud that's periodically generating a signal that you'll see propagates down here. And as it passes through these different regions, it causes them to differentiate into spinal segments. And these are morphogens that are diffusing from the edges of the spinal segments, and they're causing discs to form here that are using the same algorithm, in fact, the same simulated morphogens to grow the leg segments. But they can have different numbers of segments and different sizes of the segments. So this is all partial differential equations describing the interaction of these robot swarms and the morphogens that they're secreting and responding to. Okay, and I think I'll just put up my conclusion slide then. Skip this. Okay, so I'll just leave that up for you to look at.
All right, well, thank you very much. We'll try to stay on schedule as much as we can, so we'll keep the question session fairly short. So, questions? So,
I'll take the prerogative again. So it sounds like there's a common theme here, and that has to do with analog, right? Moving back to analog. So is that am I getting that right? And you're saying the future of computing is more looking at using like analog processes, analog physical processes to do the computation for you?
Yes, I wouldn't say that is the future. I would say it's part of the future. So I think, you know, I sometimes refer to analog computing as the other half of computing.
Mm-hmm.
And so it's been, you know, neglected quite a bit. And so I think, you know, certainly digital ways of doing things have their place. They're not going to go away. But I think certainly broadening to include analog processes will be an important part of this process. For the reasons I said, it's closer to the physics.
Good. All right. So if there's no questions from the floor, let's keep moving so that we stay on time here. So I have the pleasure to introduce Dr. Paul Krenzel. I guess we got to know each other when I was at DARPA, right? And Paul was doing some really good, exciting 3D design work at the time down at North Carolina State. He's also very involved in the graduate programs, which we had a whole separate discussion at lunch about STEM, you know, the STEM issue in the United States, which thank you, by the way, for thinking about that problem. It's a huge deal. He's done a lot of, has an august biography that I'll allow you to read here on your own. But what strikes me is he's always been very innovative on the future of design technologies, not just novel architectures, but how the entire design process is evolving and how that contributes to computing. So with that, I'd like to introduce Dr. Paul Krenzel from North Carolina State.
Okay, thanks very much, Mike. First of all, I apologize. I have a cold and a sprained ankle. So I'm kind of
You're putting in your reliever. You need to put in your reliever.
So hopefully my voice will still project well enough. It's okay?
Yeah.
Okay, great, thank you. Alright, so I came up with this title just for this talk. So I'll explain what it means in a few moments. But I'm a microelectronics person, as Michael said, so I'm going to show a very microelectronics perspective on what I see in the future. First of all, I remind you that exponential scaling is not just a Moore's law phenomenon. This is a fairly well-known graph of cost per compute element against year, going back to 1900. You can even argue it goes back to 1880. And it's an exponential curve even outside of the era of Moore's law. And there's a very strong set of arguments that this will continue. And I'm going to talk about one microelectronics way in which this can continue. We were asked to look at computing 20 years to 50 years from now. So I thought to calibrate myself, I'd look at computing 20 years and 50 years ago. So 50 years ago, this flew to the moon. It's a 2 megahertz microprocessor, but a couple of themes here. One is that there is customization in this microprocessor. It has an instruction that's only used for celestial navigation. And by the way, one can well argue, and this is a policy issue, that the microelectronic, the most important contribution of Apollo was not tame. It was the creation of a microelectronics industry that could deliver high-yielding, high-reliability chips in volume.
Who built that?
I think it's the MIT Lincoln Labs. The chips I think were done at TI. I think.
It's all in the U.S. too.
Yeah. I go back 20 years, looking at the Pentium 3. Again, a heavy amount of customization. With the introduction of the MX architecture, which is a specialized unit added for video and graphics. Another thing that I didn't put in words, but both of these systems are very memory dominated. Stan was pointing this out, memory dominates computing, programming dominates computing, and it'll get worse as we go to a data intensive world. In the Pentium 3, you've got millimeters of logic being fed by centimeters of memory. And that ratio will get bigger as we go forward. So I call this application computing because, and this is not meant to be a complete vision, it's meant to be a driving point for technology development. What I see is a large scale, large bandwidth memories, terabit memories, 100 terabit per second interfaces, feeding a combination of general purpose computing and special purpose computing, very intimately mated. The specialized computing can be analog. I'm not arguing against that, but I'll talk about digital. It continues the theme I picked up on the previous page, and a theme that's going big today with the era of machine learning, and offers big opportunities for continuation of Moore's law beyond the end of Moore's law itself. So this is my thesis that I think is feasible in the timeframes we're looking at, that we will integrate custom low volume to mid volume solid state logic and memory systems or nanoelectronic enabled ones that bring in high degrees of customization, that are intimate with the general purpose system and the memory system through aggressive 3D integration, and are intimate with a high power, a high throughput, a high capacity and power efficient memory, whether it be DRAM or whether it be a nanoelectronics enabled memory. And this is, I think, the important part of what I'm getting to. I think the time is right for certain technologies to drive the ability to do this. I think high-level synthesis from C code has been a holy grail in this industry for the whole time I've been alive. I think it can be achieved in the timeframes we're talking about through a combination of NP being able to run NP hard and NP complete algorithms on computers such as quantum computers and machine learning. This industry is driven largely by volume, and the machines are set up for high volume, the industry structure is set up for high volume, and it's all about how many zeros you can write in a check. I think it's possible through a combination of factors, both technological and policy, to drive industry to be able to actually support low and mid volume accelerators such as I'm talking about for specialized functions. 3D enablement, 3D integration will be an aggressive part of what I'm talking about, and high bandwidth 3D memories that are task optimized are also something we can do in the timeframes that we're talking about. So let's look at each of these in turn. Specialization is a very important vector for the continuation of scaling beyond the end of silicon Moore's law, whether it be analog or whether it be digital. It can bring order of 1,000x returns in performance per unit power, and potentially even in terms of cost through mechanisms such as analog, but even in digital. But we don't have, the performance per cost is a very important function. And for specialization to have impact here, design costs must become almost zero. We can't afford to do specialization by having a large team of engineers earning $300,000, costing $300,000 or more a year to design each and every specialized unit. There has to be an automated path to get to specialization. And as I said on the previous page, fabrication costs need to shift to enable cost-effective low volume and mid volume systems that are increasingly specialized. So I'm going to give a couple of examples from my own work of order of 100x to 1,000x improvement in power performance through specialization. The first one is hierarchical temporal memory, which is a cognitively inspired algorithm that we build an accelerator for. And the second one is direct from machine learning, long short-term memory, a type of recurrent network. We built and taped out an application-specific processor aimed at hierarchical temporal memory. I'm going to skip a lot of the details here, they're not directly relevant to this conversation. But a big part of this was identifying specialized functions we needed to run in order to build this to be very power efficient. I'll jump ahead of it. For example, these are two of them. A botonic sort function and a scatter-gather function. And the point is that this small amount of specialization, which I'll admit was human identified and human designed, led in itself, by itself, to 2 to 3x improvement in performance unit power for the entire algorithm. So this is an example where small amounts of specialization make a big difference in the performance and the cost of the system. My argument here is, though these were generated by humans analyzing the code and doing the design, that we're on the verge of having the technologies come together where machines can do this sort of work, and thus greatly reduce the NRE cost of doing this type of specialization. All the specialization that I mostly skipped through in the last few pages led to an improvement in performance per unit of power of 500 to 1500x, and also led to an improvement in cost in terms of silicon area. This gives an idea. This is many generations of Moore's law. One generation of Moore's law is only a factor of 2 or 3 in these dimensions. So this is many generations of Moore's law, at least in terms of performance per unit of power. We also looked at this for long short-term memory. Again, I'm going to skip the details. But the customized architecture performs 150 times better in terms of performance per unit power than the same algorithms running on a GPU. Again, very human-directed in terms of building and designing this, but it shows the potential that is there. Let's turn more to the dollar side. So if you want to get the human out of the accelerated design loop, I think that should be, I think that's a worthwhile goal. Many would be interested in that goal. It's also very hard. But I think we're on the verge of having the technology set that can do that. Runtime analysis to identify the functions we target, that's easy. We do that today. Identifying the application-specific functions and what their code is, that's much harder. There are a lot of people working on this. I believe applying machine learning to this problem has potential to actually create a solution path that doesn't exist today. Getting near optimal circuit design from the high-level code is also something that we need. Again, this is very hard. We're not at the point where we can do this. But I believe that factors like being able to run NP hard problems on a quantum computer and get exact solutions or near exact solutions, or similar approaches to that, have potential to solve this sort of problem. So for example, one thing that we're actually doing is looking at solving what are considered to be NP hard and NP complete problems on a near scale, noisy quantum computer. This is IBM, so we're working with IBM on this. So we're looking at replacing heuristics with near exact solutions for EDA problems, such as those that enable optimal design. One problem we've been looking at is a balanced min-cut, which is used in a lot of circuit and layout problems. And the exact solving exactly is NP hard or NP complete. But solving it approximately, but not with heuristics, is possible on a combination of a hybrid on a conventional computer and a near scale a noisy intermediate scale quantum computer. And right now we're doing the programming to show this. So this is work in progress, but I think it's feasible and it's an indicator of the potential here. I'll skip some of the details here. Low cost, low value fab. This is partly a technical challenge and partly an organizational challenge. The equipment, the business model, everything is organized in the fab industry towards very high volumes. There are alternatives, cluster tools rather than high throughput tools, business models that reward low and mid-volume manufacturing. And frankly, time's in my favor here. 20 years from now, 3 nanometer will be an old technology that's been completely paid for. So that will dramatically reduce the cost in of itself. But there's organizational and technical issues here too. Let me turn to the applique part of what I'm talking about, that is intimate 3D integration. There's a couple of technologies here that are still in early stages, but have great potential. One is called hybrid bonding, where you can interconnect chips face-to-face at 1 micron pitches and below. Another, a fine scale through silicon vias, which Mike is very familiar with. But we're getting to the point where, again, we can get down to 1 micron, well, 4 or 5 micron sort of pitches for very high density vertical connectivity. We had a project funded by Intel looking at applying these technologies to computing. What we did was intimately integrated 2 processes together using fine pitch hybrid bonding so that the compute thread could move between them on a cycle by cycle basis to optimize the throughput. Now, I'm not particularly suggesting continuing that project for the next 20 or 50 years, but replacing, but replacing one of these with an accelerator function that has all the resources of the CPU intimately tied to that is what I'm suggesting is a way to deploy accelerators with general purpose computing in a way that leverages the infrastructure of the general purpose computer. This project, this is the SEM of the project, 2 chips face to face with the hybrid bonds they're shown in the middle. And this worked, the chips worked, which is always good in academia, and by themselves had a significant improvement. Though I'm not arguing continuing this project. What I'm arguing is this is an example of using this technology to create 2 chips or a chip stack that work together very intimately. Skip those. So this is what I'm arguing. Instead of a second processor, stack an accelerator that has a special purpose unit designed using the techniques I was talking about before, that has direct and fast access to all the CPU resources, and most importantly, to the memory bandwidth that is integrated with the CPU. And these can be digital or analog accelerators, depending on what you're able to design and what is the best solution for a particular problem. And you can use thin die and TSVs to keep adding these layers. And by the way, one technology here that barely exists today is doing this at the chip scale. Today, this is done at the wafer scale, which brings in lots of constraints. But doing it at the chip scale opens up the door to doing this sort of vertical 3D integration of specialized functions. The final leg of my triad that I'm talking about here today is specialized 3D memories. We've been looking at specialized 3D DRAM that can achieve greater than 100 terabits per second. There are many applications that need this sort of DRAM even today, and an investment not even just in DRAM, could be storage class memory or emerging nano-enabled memories that give a combination of high capacity and high throughput with power efficiency are fundamentally important to this industry. Again, remember, a modern computer is a massive memory feeding a small amount of logic. And so the memory itself is very important. Give some examples today of the mismatch between memory and the applications. HBM2 is the highest bandwidth memory you can buy today, 256 gigabytes per second. In contrast, the Google GPU, if you want to actually use all the compute resources there, need these sorts of memory bandwidths for multi-layer perceptrons and long short-term memory. Our long short-term memory accelerator that we built needs up to 1 terabyte per second of memory bandwidth in order to be used at full capacity as well. So this is even a shorter-term argument that we need specialized, task-orientated, 3D high bandwidth memory to enable better computation. There are a lot of problems that need these sorts of solutions. FFT and synthetic aperture radar, MRI image construction. Here's a paper which specifies some GPU challenge benchmarks that are very difficult to solve on GPUs, and largely because they're memory constrained. And a lot of these are physics-based problems that are always the classical problems we roll out when we talk about building better scale computers. We did a design exercise with Tesseron, adapting their DRAM 4 to enable this sort of paradigm. This is a slide from Tesseron, and again, I'm not going to go through this, but we're happy to leave it in the slide set. What we did is modified the bank interface to expose a lot more memory bandwidth. We employed dense TSVs to create wide buses in the 3D structure. And we did some other logic level changes as well. What we basically were building was an array of 64 high bandwidth memories. Each memory could feed up to 2 terabytes per second in each direction. And that's each bank. There's 64 of these across the chip stack. And so altogether, we actually had 131 terabits per second of peak memory bandwidth. We've also done a design exercise looking at doing this for a more conventional memory structure than Tesseron's. And even in that, we found that we can get up to we can have a sustained throughput of a terabit per second. And sustained is very different than peak. It's much harder to get high sustained throughputs through specialized design of the 3D memories, even using more conventional memory options than tesserons. And again, I'm just leaving this in. I'm not going to go through all the details. But the point is here that a specialized 3D memory can dramatically outperform the commercial state-of-the-art memories, which and with applications that need it, and can very dramatically outperform SRAM, which actually isn't a high bandwidth technology. It's really a low latency technology. So that brings me back to my thesis, that one vector that allows to continue on a Moore's law type exponential curve is increased use of specialization, and the key is providing the technology set that enables that. Integrating general purpose and special purpose compute functions by leveraging those specialized processes using evolutions of today's 3D technologies, and creating specialized, intimate, fast, low power, and very high bandwidth memories are all keys to enable computing to keep on an exponential growth curve in both cost, power, and throughput. And this is the technology sets that I was talking about: near optimal automated accelerator design, low cost, low volume chip design that can be 3D integrated with general purpose computers, and specialized high bandwidth 3D memories that are task optimized to enable this continued exponential curve. That's the end of my presentation. I'll be happy to try to answer any questions. Thank you very much.
Okay, so a lot to think about. This was probably the most sort of specific, right, of the various lectures. So questions from the floor, yes?
I was wondering where the technology that also has help enabled here is the thermal dissipation. You've got a lot of power going through these
That's a very important question, important issue. And it's a very fundamental issue. It's hard to deal with. Particularly when you're integrating memory, particularly DRAM, you want to operate at 85 degrees C, not 100 C. So in this sort of system, that frankly feeds you towards liquid cooling type solutions. Of course, there's been big investment in that area lately, so there's greater feasibility of actually deploying those even in fielded systems as opposed to just centralized computers. There was the iSchool program at Dartmouth in particular. But yeah, liquid cooling, or the system is small enough that the power is constrained sufficiently. Yeah. Or analog computing type functions that can be very low power and thus enable the memory to operate at 85 degrees.
So if you can synthesize a couple of these different pieces together.
That's one important solution eventually. Yeah.
Memory, power. Right?
Yeah.
Okay, I've heard that for a while. So
And
yes.
cost.
And cost, let's not forget that. So
So what about Rent's rules with your 3D connectivity? How I mean, what's the sort of sweet spot in terms of getting your 3D connectivity as opposed to just taking up all of your volume with the energy?
So what we found with the Intel project is we actually didn't need the highest density that the technologies could allow. We did a trade-off study, and we found we only needed 8 micron pitch. We didn't need the 4 micron pitch that was available then. Once you get outside of the logic, Rent's rule changes. It changes to how much memory bandwidth do you have, and hence my argument there. But within the logic, the 3D solution, the solutions I'm talking about basically are very close to giving the vertical connectivity pitch to be equal to the wire pitch of the top metals. Close. Not quite there. In a separate talk, we've got a slide on that. Yeah. That's an important thing. Thank you.
So I'll take a prerogative too. I'm actually sort of ask almost a business-oriented question to a group of academics, right? But this is actually predicting this is an important thing. So we agree that the trend toward customization is very important, and how will we accomplish that? Do you think the existing legacy players, I mean like the foundries and people who've traditionally done this, they're the ones who are going to capture this business, or is this going to be an opportunity for people to come out of nowhere and take over this customization paradigm that you're talking about? Are the legacy people doing this, or are disruptive people going to do this?
Well, some of the legacy people are interested, such as Intel,
Yes.
with the Stratix 10E bit.
Okay.
So there is some interest because it enables selling of other parts within their ecosystem.
Sure.
But from a pure custom perspective, it is not the legacy players that are interested.
I'm intrigued because they might get scooped. They might get scooped on this if this is the future, right? They could get scooped by people coming out of nowhere and saying, "Look, I'm going to base my whole business on low volume customized stuff."
That's a difficult business plan to execute.
No, I know, but I mean, I think there is some.
I think there is an argument there. You're seeing there's a lot right now of machine learning. There's a lot of specialized processes out there.
People are becoming chip people who never built chips before,
Yeah.
right? Everyone's getting into the game. Right?
But I mean, I haven't found this in our 3D work. You go to Global Foundry with a $100,000 check, and there's not enough zeros in that.
Good. Okay. Fascinating. More questions?
Are you saying there's a commercial avenue for specialized optimized chip designs within a larger structure? Is that what your comment about Intel was just?
Yes. So what Intel is selling, well, they seem to want to be able to sell. I don't think they're actually selling it yet. Is you buy a Stratix, a high-end FPGA with what's called the silicon bridge technology, the ENIB technology, in which you put a chiplet on the other end of that silicon bridge to do a specialized function, and that chiplet is custom designed for that specialized function. So that's kind of an early example with using 2.5D technologies of what I was talking about in pure 3D.
And that's an interesting confluence with government needs, right? The whole thing is it possible to have a commercial business model based on customized, modest volume? I'm just fascinated by some of these ideas. So Stan.
Well, I mean, just to comment on that, you just described the TSMC business model. They don't have chip designers.
Yeah.
They just manufacture. You tape out. You send your manufacturing files. And what they do is they give you the PDK. You design that PDK, and they'll make however many or however few chips you want, as long as you can sign the check.
Yeah, as long as there's enough zeros on your check, that's true. Otherwise they'll throw you out. I remember I was actually visiting TSMC years ago on a government program. We kind of got politely thrown out, but anyway.
but actually, they're working all the way from 180 to 7 nanometers.
Yes, that's true.
So it depends upon
Broad
what you want.
portfolio of technologies.
Yeah, so the argument here is through a combination of amortization of the costs, maybe some tool changes, and some business changes. You can do low volumes in that fabless paradigm.
That's fascinating, because that's a confluence with government interests. I think I'd like to suggest that the panelists all come up, because what I'd like to have is sort of a real panel now with an interactive panel. You've got like really smart people that are working the future of computing. This is your chance to like tap into their collective intelligence, right? Which is a really cool opportunity.
I'm not sure our collective intelligence is
So I'd like to thank everyone again for taking the time out, not just the panelists, but also the attendees. And as I said, there are quite a few more people that are interested that will watch the video, because in Washington, it's just busyness is one of the challenges that we all face. So themes. I mean, I can prime the pump, or are there general questions on the general term, like connecting themes between what people talk about? So in the middle.
You talked about the resurgence of analog computing a lot, and certainly the quantum people are really aware of that. But that reintroduces a lot of old issues like error correction. What do you see if we have a move like that? How are we going to deal with things like greater difficulty with error correction in these new technologies?
If you're doing the types of calculation that I'm talking about, you don't need error correction. I mean, error correction, you want that if you want a very, very precise result.
Mm-hmm.
If you're only interested in a result with, say, 3 significant figures in a decimal system, all that other stuff just sort of falls underneath the overall computation. Now, that said, there are ways of taking the types of things that I talked about and segmenting them and essentially constructing something with any precision that you want.
Mm-hmm.
But the fact is that most of the new computation today doesn't care about precision. It wants an approximate answer with some bounds on that approximation.
But the old computations still matter.
They do, but somebody else will take care of that.
I'm
Right?
just,
As far as I'm
So
concerned.
it's a market segmentation.
You know, the digital computation is not going to go away. It's, you know, it's here to stay. It'll always be here. I would say that what I'm looking at is an area that is growing dramatically. I believe it's going to actually dominate all of computation. I think eventually 99% of computation is going to be in this stuff, and 1% is going to be in the high precision. So I'm looking at what I think is the larger chunk of it, and trying to put as much into place as I can in the next 10 years, because after that my brain will have turned to mush, and I won't be contributing to the field anymore.
So I'd like to provide an example. The thing that triggers in my mind, what Stan was saying in your question is, look at like Watson, right? Like when they played Jeopardy, right? I saw the set at IBM. It was pretty cool. They left the set up for a few months afterwards. I actually had Jennings's button in my hand. I hope some of the intelligence rubbed off. But that's an example of here's a bunch of answers with probability, right? Sometimes they're right, sometimes they're wrong, but it's just an answer with a probability.
And the brain uses about 1 digit of precision. So very low precision, but massively parallel analog computation is a lot of what the brain does.
So I was going to offer that if you think about it from a computational paradigm in which we have to program the machine and tell it exactly what it's supposed to do, then the components better do what it is they're supposed to do, or we're never going to be able to get it to do what we want. However, if you're relying on its internal ability to organize itself or its internal dynamics, then you've got a different question to ask, which is, will it organize around and with all of the imperfections or not? So I think that's the basic difference. In neuromorphic computing, which has long dreamed of building analog neurons, for example, is stymied at the small node sizes that we are now because of the variability. But they also still have a computing mindset about how they're going to use the devices.
Yes.
You know, profits are never very well received. And
That's true.
They're usually thrown out of town.
Usually
Actually,
Tell us about it.
they're usually thrown out of town.
Spell it with an F.
as Yogi Berra used to say, prediction is difficult, particularly about the future. What, on the policy level, are you seeing in resonance in terms of either commercial or national R&D budgets? Because I'd like to see this reflection in increased R&D investments, particularly in this country.
I'm seeing exactly the opposite. They're all going, especially from industry, R&D budgets are going down. The issue is that within the boards of directors of the technology companies, the current paradigm is companies shouldn't be doing research. But that's something for somebody else to do, and then companies will take advantage of it. And so R&D budgets just keep getting chopped to smaller and smaller levels, and then in the government, I think that we jump on bandwagons, and we want to put, we say, okay, this is the absolute greatest thing that we can be doing, rather than trying to create an investment portfolio. I mean, you get wealthy by having a proper portfolio, and yeah, you want to make sure that you've got your investments kind of split around. But I think we tend to get on a bandwagon, graphy. Throw every dollar you got at that, and then
I'm a little sensitive to that one, Stan. I'm sorry.
then everything else gets starved, because everything's going on to what's the latest fad.
So I'll offer a couple of comments too. So I find that the NSF is excellent at supporting well-established paradigms, and they continue to invest in those paradigms, and they develop very deep, sort of wells or whatever in various areas. They're a really hard time doing new stuff. DARPA, I think, is kind of a mix. It could be good at doing new stuff, but its perspective is pretty short term, and it's usually mission focused. So it also doesn't go after the longer term basic stuff very well. In fact, you can even see them, in the recent past, it seems like they want to emulate venture capital more and more, and I keep thinking, well, that's not what we need DARPA to do. We've got tons of people in venture capital. That's my own opinion. So I've thought about this a lot, and a good place to me that would seem to reinvigorate the field of computing, people may shoot me here, is the national laboratories. Because they have, professional staff, they take on very long-term problems, they usually have fairly stable budgets. I've been preaching this to them for probably 10 years, but I really haven't seen it take hold yet. Yeah.
Question in response to that, you've been preaching this to them for 10 years. As someone who supports the Department of Energy, the national labs, A, have a specific mission, and Office of Science, which funds them, has a specific mission, and then B, they have their national lab culture, both of which probably need to be adjusted to. Any thoughts from the panel on
You mean we
those
need
two
to
issues?
adjust to them, or they need to adjust to us?
I mean, people have been trying to get them to adjust for years.
So I back off just a little bit, but I think we need another Sputnik moment. Where someone gets scared enough to say that we need an.
I think it
And
will
the China's $100 billion, and the China's $100 billion.
Listening to what Stan was saying and stuff, we might not have to wait that long.
But also, I've been reading the book New Space, and it points out that when you create the right incentives, you can make advances without 300% overheads. And the 300% overheads are largely driven by regulation. So there are, I almost don't want to say this, but there are ways of getting more bang for our buck, even with what even with in the current budgetary environment, and the way the way NASA is handling the space entrepreneurs is one way in which one way to look at that.
So with regard to your question, I'm reading a book now called Loon Shots, and it's kind of a history of grand technology projects, both in government and industry. And it's written by a physicist who also, which is why I like it, which offers a lot of perspective on how it is you have to correctly couple the small, innovative, organization with the large franchise organization, and that you can't have them incorrectly coupled, because if you do, you kill everything. So the problem with the national labs is that there's essentially a very large franchise in which absolutely no one is motivated to do anything dramatically different. It can only hurt your career. And so nobody does. And the same is true of most large organizations, large companies and so forth, which is why startups exist, right? That's why startups come along, because it is in your interest to behave differently in a startup. I've been in many. And so you take large risks, because you know that if it pays off for you. Take a large risk in a big organization, it doesn't generally pay off for you, so nobody does it. So I think the ideas are there about how we could organize things differently. You do need the large franchise organization, because it's the one that ultimately has to provide the money, basically, right? And it also is the one that understands what the application domain is. It has the application expertise. And then you got a bunch of crazy people over in a lab, and you motivate them to do something, dramatically different. And that's what we would need to do here. That's what we did in the Manhattan Project, right? It's what's always been done when you have a big new opportunity. So that's my 2 cents on it. We're not very well organized.
I would say that there's examples of that thing, and they need to be physically different. If you have a big organization that wants to be innovative, you have to throw your crazies elsewhere, physically elsewhere, so they don't fight with each other.
Yeah.
Great example, because I knew some senior people at Intel who explained to me the early days. That's why the crazy microprocessor people were exiled to Oregon. So they couldn't impact the mainstream memory business. They couldn't infect the mainstream memory business with their crazy ideas. So that's an example, right? But you have to separate them, I think.
Another example was Xerox in the old days.
Yeah, well, yes.
They threw the people into Palo Alto and said, do what you want to do, and they funded them, which I could never understand.
Yeah,
No
that's
intention
a
of
great
ever using the technology.
I just read a great book about FARC.
So their copier company is what they ended
Yeah,
up
and Xerox never really used the FARC.
Now, with
innovation.
regard to the Sputnik moment, there was a theme I heard today that the revolution that caused an enormously exponential change in our way of life, in our investment strategies, in our strategic positions, was computing.
Yeah.
All right? Developed, by the way, in response to a need, ultimately, for us as a nation to get visibility into a denied area called the Soviet Union. That was the genesis of it all. Now, what are we doing to address the strategic challenges of the next generation. And portraying this, as Potomac Institute is capable of doing, as we're at the end of that compute cycle, or approaching the end, or partially. We are about to lose major strategic advantage. So what do we do to characterize that as a Sputnik moment? It's hard. It's a hard sell.
That's a tough question.
Well, we're no longer the best. Well, look at the examples. We're not the best in some key areas, right? Or we have either serious competition, or we're in second place, or beyond, or less. That should wake us up alone. That should be a headshot.
But the VC example is a good one. You know, we're all, even the government now is seeking to become VCs. Well, VCs' purposes are to start a company and then sell it,
Yes.
not to develop
The highest bidder.
technology.
Mm-hmm.
Anyway, you were.
No. That's a good comment. Yes, Mike.
So I really like the idea of generative design, where you can ask a computer to design a bridge and it'll give you different materials and designs based on optimizing different factors. And we were talking a couple weeks ago about, well, what if you asked a computer to design something that computes? Would it come up with technology that we know today, or would it come up with something radically different? So I just wanted to see your kind of thoughts on that.
With today's machine learning technology, the best you can probably do is imitate the way that something else does it, right? Using generative networks. And so if you have the training examples, there's not even training examples. If you have that model, then you can have a system, create another system that generates solutions in a similar fashion to the original one. And that's kind of the part of what the next level talk down of how one way to get towards what I was talking about. We're having machine learning identify and do the high level design of what you want to accelerate. So this doesn't exist today, but the generative network aspect does. So I think that's possibly the genesis of how to get there.
I might mention one example that some of the rest of you may be able to fill in the details, because I'm kind of hazy on them at this time. But back in the 90s, there was a project in England using genetic algorithms to design circuits. And so genetic algorithms, if you don't, sort of a simulated evolution. But they were actually building the circuits and then testing them, and then depending on how well they performed, they would then feed it back into the genetic algorithm. And they got some circuits that were doing very well. But when they analyzed them, they couldn't figure out why they worked. Because they were using essentially non-circuit connections between the components to accomplish their function. So there's a case where a human designer, would never do that. In fact, that would be considered a problem. But the machine, with no preconceptions about what an electrical circuit should be or how it should be designed, made use of these other sorts of physical effects.
Does this ring a bell?
Yeah, no, absolutely. It points
Very much
to
inspired me, yes.
and it points to sort of a problem or an issue. And a much more recent example is AlphaGo versus Lee Sedol. The reason that AlphaGo beat Lee Sedol 3 times very easily is that through a gigantic number of games that AlphaGo played against itself, it discovered a brand new strategy that no human being had ever thought of before in terms of playing the game of Go. Traditionally, human beings capture the middle and work out from there. AlphaGo figured out if you capture the corners and then move in from the corners, you can actually beat the center strategy. And so they sprung this on Lee Sedol. He'd never seen it before. And in 3 games, he got wiped out. However, on the 4th game, he had figured it out in his own head. So it only took him 3 games to figure the strategy out. It took AlphaGo maybe 100 million to invent it. And so on the 4th game, he beat AlphaGo substantially because he had figured out the strategy. But then that night, the AlphaGo people ran another 100,000 games and came up with a new strategy.
I'm going to argue with your word strategy. What they did is they came up with a new way to index.
A new pattern, yes.
Okay.
You are correct.
Okay.
You are correct. It's strictly pattern recognition, but it was a new pattern.
Right,
a
exactly.
new pattern.
So we humans call a game strategic when we have to meta-organize it in our heads. And what happens is the moment that you have a lookup phenomenon, because what does AI really do? It exchanges search for knowledge. There's no knowledge in an AI. It's always search. And so what happens is you go, you make a big search. Well, now we've got a problem. Because if AI does a big search, then that means that the numerator is 10 to the x. And when I put 10 billion processors on it, I mean, I love your approach because essentially it is better than that. But if you put 10 billion processors on it, you're just doing x minus 10. You haven't solved the fundamental problem. So what we have to do is we've got to divide the numerator, right? We've got to divide the exponent. The only way you do that is either with something like a thermodynamic abstraction or that self-organizes, or your memristors, because what you're really doing then is you're making a meta structure. And the meta structure then takes x and divides it by 3, because it collapses the space to a different representation. And then it divides it by 2, because you've got another bank that does a different thing. And when you do that, you end up with an algorithm that's 10 to the 1500, which, by the way, is the typical number of states in an Avalon Hill war game.
Yeah.
10 to the 1500. You couldn't do that in 100 decades, but you can using a memristors and a matrix representation, because what happens is it's the whole surface.
I wanted to go back to your question, though, about what motivates us. And so here's a thought, though. I think it was mentioned several times, a lot of the big core ideas that are going on in computing now have been around for 50 years or something, right? Even the machine learning stuff hasn't been. And it seemed like, though, it took us this long to get all the pieces together to somehow, use it. Well, some of the ideas that we talked about, particularly the three of us, I contend that if we had the ideas, that the path would be much faster than the 50 years. It wouldn't take 50 years to implement the ideas, because we basically have the fabrication technologies, we have the skill sets, we have to train some people and so forth, but the jump could be very fast. And when that big jump comes, and you suddenly get orders of magnitude increase in compute capacity, that country has an enormous win economically at the very least, right? And with that economic win comes the rest of everything that we want and need, in my opinion. So that's what I would say. And if we don't get it, if the Chinese figure it out first, because they're investing heavily apparently in the space, then we're playing catch up. So what do you want to do?
Well, let's not be demonizing the Chinese.
I know.
It's a very rich culture.
Yes.
The Communist Party of China is another issue. But they also own a good fraction of the people in the world.
Yes.
So in terms of markets or just serving people. But it occurs to me that, as you're right, we tend to chase shiny objects. And the three shiny objects that I see right now is AI, which is talked about by people that don't know anything about AI. It is quantum computing, which nobody knows anything about.
Even the people doing it, yeah.
That's true. It's not a thing. Quantum computing is not a thing. You've got to go to 0.035 Kelvin. I'm sorry, that's not a thing.
But let's face
Actually, but
facts.
it's analog.
Let's face facts.
It's analog.
What was the third shiny object?
The third shiny object is bioengineering.
Is what?
Bioengineering.
Bioengineering.
What I saw represented today is an approach that incorporates fundamentally all three of those, that underlies all of that. And I contend if we go discover life in another place, and it happens to be different, but responds to a set of potentials that are not the potentials that generated our life, that could be a moment.
That'd be a big moment.
And people will come to you and say, why is this? And you can say, well, I told you so.
It evolved.
But I'm wondering whether the advances in fundamental approaches to computing, or what we call computing, isn't really the essential basis on which all of these shiny objects are being built, with no hope of getting there, without the kind of improvements you're talking about.
Well, several years ago, I went to a meeting sponsored by the National Academy of Engineering, and it was pretty remarkable. There were people there who were talking about wanting to have a grand challenge for clean water, for renewable energy, for food distribution, all of these great things. But every single one of the people talking about these grand challenges said, and we will get there when we have better computers. And then I got up and I talked about a grand challenge for better computers. I mean, everyone was looking around the table, and it was almost obvious which one was going to win the grand challenge competition, because the computers were the essential part for all of the other things that people were talking about, because it was all about distribution or optimization or whatever, and nothing that exists today could actually solve those issues. So, I think that's one of the things that motivates me. I think that there's just a lot of significant problems, and they are beyond the ability for individual or even small groups of human beings to just even get a grasp on all of the variables involved in the system. And so I think that we just need a tool that helps us sort the actual correlations from noise and give us a better direction on which way to solve the problem. And I will say that I agree with Todd on everything that he said from the technical point of view. I have one significant difference with him, though. I don't want an intelligence to evolve. I want to design the intelligence, and I want to corral it and limit it, because I want it to be a tool. I don't want it to get away from me. So that's,
So you should watch my TED Talk. Yes, I get it.
Yes.
Of three general categories of thermodynamics, biological and analog, would best be a computer that can solve the problem of predicting hurricane paths? Is that a discussion we can entertain, or is it?
I think that would be an interesting hybrid. I think you need simulation, so you need physics input. That's best determined by simulation. But then, instead of running a particular simulation like is done now, and I'll call it a well, no, I mean it's just running 1,000 different simulations. What you can do is, by taking a few general principles from a simulation, you can start to analyze probabilities. And then I think a Bayesian approach with the right data set as the priors would actually be far more efficient than just running a physics package thousands of times.
So I'll give a slightly different answer. So I think that neuromorphic computing systems, forget about the thermodynamics stuff for the moment, and others have proposed this, read papers about it. They should be very good at multi-spatial temporal scale simulations. Okay, in other words, you only spike when something changes enough that you should spike. And so therefore, some groups of nodes may be spiking rapidly and some may not be spiking. But that's not what computers are designed to do today. Today we just basically update the whole state continuously and burn tons of energy in the process. Okay? But I think that a neuromorphic system, spiking event-based system, could be an excellent thing to do things like the simulations you're talking about, because that is a multi-scale system, right? You've got stuff going on at the small scale and at the large scale. And if we did it well, we would have a much better simulation engine than we have today. But we don't, nobody's really doing that. In fact, I thought about doing a DARPA program on that.
Mm-hmm.
So I want to sort of maybe summarize something what I've heard. I'm putting sort of the hat on if I was a government official, sort of the senior government official thinking about strategy. So clearly the classical, and actually I sold DARPA programs based on charts that Moore's law is ending. So I was like the gloom and doom person already 10 years ago, right? So clearly, I mean, it is, right? And people are trying to squeeze water out of a rock. So now the big question is, and everyone's catching up with us. That's what happens when a technology matures. Nuclear weapons matured and people caught up. I'm sure they spied too, but they caught up. So people will catch up. It's inevitable people will catch up, whether through stealing or through work on their own, whatever. They will catch up with the classical Moore's law scaling. So it looks like what I've heard is there's a lot of opportunity in various analog paradigms, right? For many orders of magnitude improvement. Those are areas we should take seriously as a government who can take a long-term view, who can take a view of like 20, 30, 40 years or more to make sure that we're on top. Or that's one of my takeaways, and maybe I'll throw that out to the panelists for their comments. I mean, one of the things we do is provide strategic advice to government officials, right?
One point I would add to that is that I think where analog is going to be most useful is in those areas where it has distinct advantages. So low precision we talked about already. I think massively parallel. Again, if you're simulating a low-dimensional dynamical system, you can do that with a digital computer much better. And I think that's probably still good. Maybe not always with the same power advantage, but I would argue that low precision, massively parallel analog computation is one of the areas where it can really give us some success.
Going back to your point, I'd argue that a precise PDE solver needs to be solved digitally. I don't see an analog computer for that. But I think the Stan's combination.
There have been though, right? Historically.
Large scale?
No. Well, large scale in terms of spatial resolution, or?
Large scale in terms of the number of cells that you're modeling.
Well, they're continuous, so there is no number of cells, but there's a spatial resolution.
Yeah. But I think, to address what you're saying, I think you have to go back to what Stan's presentation was, that you have to combine it with new devices. You need precisely programmable resistors are very valuable because they save a lot of area and they save a lot of power.
So I think that analog computing as a place to hang your hat is insufficient. That it's a red herring, basically. I think that if you combine analog computing with these other ideas, like using the physical dynamics or the thermodynamics of them to learn a dynamical system, then it makes sense. But as a means to do memory in a computing system, people have talked about that for what, 50 years?
Yeah.
It doesn't. I don't think it goes. I really don't.
Well, I agree with you, and this is a fight that I had when I was at Hewlett-Packard. You know, when I first came up with the memristor, my management was all saying, "Okay, great, make us a memory."
Make a memory out of it.
And what I kept telling them was, you know, that's not what this is going to be good for. It's going to be good for computation. They said, no, I mean, you know, that takes too much effort. Make us a memory now, and then we'll talk about, computation at some point in time in the future. So what Todd says is right. And the thing about these memristor devices is they're nonlinear dynamical systems.
And they're thermodynamic because they change state depending on how much energy you put.
That's correct. And so one of the things I'm trying to do is pull together nonlinear dynamics with non-equilibrium thermodynamics and really understand that particular issue. But it's not the fact, what I tried to do is I tried to say, okay, there's all of these things when taken together are powerful. In-memory computing, it's analog, and it can be reversible. And so when you have all of those things together, that really makes a difference. And also, it's dynamical.
And I want to throw in the comment about the reversible pieces, is that, again, I think reversible computing by itself is an insufficient concept. It's been around for a long time, and nobody's ever figured out how to do anything with it. However, it's a natural part of the thermodynamic concept. It's just one part of the thermodynamic concept. Reversible computation thermodynamically simply means you're not throwing away the conserved quantities, you're just sort of sloshing them around to try to find a lower energy state. That's what reversible computing is. The difference that when I try to explain this to people who aren't physicists, I say, when you go into a meeting of various people, let's say you're working on a project, right? And you go into a meeting with a bunch of people, and you're saying, well, this is what I see, this is what I see, this is what I see, this is what I see. And what you're trying to do is create a common understanding among you, all right, about what the low energy state is given what you currently have. But it's reversible, okay, because you haven't made any commitments, yet you're just having a meeting, all right? And so after the meeting is done, if everyone agrees that, yes, we have found a low energy state, then what you do is you say, okay, then I can make it better by doing this, and you can make it better by doing this, and then you go off and change stuff, right? You buy things, you hire people, you commit yourself to deliver something. Those processes are irreversible, right? So this goes on in daily life all the time. Now, if you're in the meeting and you're having this exchange, and you realize that we're not in equilibrium, there's something we don't know, then what happens is you go have other meetings with another group of people, and you try to resolve whatever the issue is that you couldn't understand. And so what happens is, in the reversible process, you rapidly try to find an equilibrium state, all right? And once everyone says, yep, I'm in equilibrium, then you make an irreversible change to improve that state in the future. That's a natural consequence of any thermodynamic perspective on computing. But analog computing by itself is not. Neuromorphic computing by itself is not. Reversible computing by itself is not. The reason I keep hammering this thermodynamic idea is that this is the foundational piece that's clearly missing, and that if you can, with effort, put together all of the pieces of all the things that people have talked about for 50 years but that don't yet work. And that's why we've got to invest in the theory. We've got to get some smart people who are going to write a bunch of stuff that most of us don't understand. We got to get some people who are going to translate that into simple model systems, the kind of stuff that I was trying to do with my thermodynamic neural network, so that we can see it. You got to get people like Stan building devices and small-scale systems to get started that show it. And when we have those pieces, then we can build, I think, coherent, large-scale systems, and we can do it quickly because we have all the tools. We can already build the devices. We can do that, but we can't do it if we keep screwing around with the same insufficient set of ideas that we've had for the last 50 years. If we knew what we were doing, we would have already done it. I get off my soapbox. Yeah.
Good. So, final thoughts from the audience. I know we went a little bit over, but I think it was a stimulating conversation, so I didn't mind. I hope we respected your time, but yes.
Let me ask a question that will extend this by several hours.
Oh, man.
Is there anything about the single thread approaches or the combined approaches, which I tend to look at, that is inherently more secure?
That is a multi-hour discussion, yes.
I think it is. Because if I mean, I can put all the electrodes I want into your brain, and I'm never going to figure out what you're thinking.
But there are definitely approaches to essentially doing all this computation in an encoded manner. So yes, there are specific proposals that have been brought forward to essentially combine I'll call it a set of a security vector that's required to actually translate what's been going on into something that somebody can understand. So that's something that people are actually working on actively.
But you can also train the system that will spoof the code.
Yeah.
Yeah.
That's true too.
Yeah.
So, Paul.
Very, very short kind of statement about possible avenues for moving forward. The Department of Energy Office of Science had a request for information. Unfortunately, that's closed now.
I responded.
Great. So, I mean, hopefully those ideas are being heard. They intend, at least, like that's the anticipation from the RFI, that some sort of funding action will move from that. The Department of Energy also created an Office of AI. I know AI is a buzzword, but if they're creating an entire office around it, that means they've got a pretty broad scope of things to work on. So 2 new avenues of hopefully getting ideas heard and getting funding.
So I wanted to thank, I know we went over in the room we have for a limited time, so I wanted to thank everyone. I wanted to thank the speakers for their participation and the patience with going got the juices flowing, and also thank you for the people who are here in person, also the folks who may be listening in, and people who are yet to watch the proceedings here. I know 3 hours plus is a huge chunk of anyone's time in DC here. Hopefully you got something useful out of this experience.
We will have the video up. I think the protocol is we plan to have this uploaded and connected so people can watch this who are interested in the subject, and hopefully it'll influence their thinking on strategy.
Thank you, Michael, and thank you for the.
Thank you.